Okay, let's get started. We have a lot to cover today. And the lecture is, well, you're not surprised, right? The lecture is titled Emerging Memory Technologies, and you may be wondering, the in-memory computing is also emerging. That's true, but we're going to finish up the emerging in-memory computing part and then move to really emerging memory technologies like phase change memory, spin transfer torque MRAM, memristors, which you may have heard of. This is a quick recap of the last lecture. Basically, we talked about memory latency, continued that, and your homework has some readings if you choose to do them. We talked about understanding and exploiting DRAM latency variation. And again, even though we talked about this within the context of DRAM, this variation exists within the context of all types of memories. So keep that in mind. It's very fundamental. And we talked about memory latency, voltage, and reliability relationship. And then we started processing in memory and spent quite a bit of time on that one. We talked about how to minimally change DRAM to do some computation. We started with copying, initialization, the bitwise majority function, and or not, ... And then we moved to doing computation in the logic layer of 3D stacked memory, much more comprehensive computation, because we said that if you want to add a processor or significant amount of logic into the DRAM chip, it's not easy to do that because your process of manufacturing the capacitor is very different from the process for manufacturing the logic. Okay, today we're going to finish processing in memory, talk about some simpler approaches, but I'm going to pick up on where we left last time, and then talk about some other issues. There's a lot in this direction, and this is a very, very active research area at the moment. So it also, as we discussed, it spans all the way from devices to algorithms, maybe even problems. How do you specify the problems into algorithms? So we're not going to be able to cover everything, of course, clearly. And emerging memory technologies actually plays into that also, because there are people looking into using some of these emerging memory technologies to do better processing in memory. We may or may not talk about that, depending on where we come. And we'll talk about hybrid memory systems after we start emerging memory technologies. Sounds like a plan? Sounds good? OK, perfect. Well, this is what we're trying to do, basically. This is what we're discussing, basically. Processing in memory is good for latency and good for energy. And as we've discussed, you can hide latency, and we're going to talk about some of those techniques in the future. But it's very difficult to get low energy by moving around a lot of data. OK, so this is just to remind you, this was our observation. High latency and high energy is caused by data movement. And we want to minimize data movement by performing computation directly where the data resides, as close as possible. And as you get farther away from the data, your energy and latency increases, obviously. And you've seen this, for example, in the row clone, right? If you copy data between two rows in the same subarray, that's the fastest and most energy efficient. If you go even to different subarrays or across banks, now the benefits of copying data within DRAM reduces significantly. If you go across DRAM chips, now your benefit reduces even more. If you go all the way to the processor, your benefit reduces more. If you go to another processor, your benefit reduces more. OK, and you've seen this, so this is just to jog your memory very quickly. And again, I'm still jogging your memory. None of this should be unfamiliar. OK, and this is why we're looking at it today, because today there's a huge problem with the technology that we've used to building memories with, DRAM. And also, there's a huge problem with the applications and systems where data access is a major system and energy bottleneck. It causes energy problems, and systems are very energy limited. And data movement is much more energy hungry than computation. OK, I think I'm almost done jogging your memory. But we were looking at two different approaches to in-memory processing. One was minimally changing DRAM. And again, you can think of this as minimally changing some other memory technology. Maybe you can think of that later as phase change memory or STT-MRAM. I don't know. Somebody may be interested in doing flash. But we're not going to talk about those. But we left off somewhere over here, basically. We wanted to exploit the control logic in 3D stacked memory to enable much more comprehensive computation near memory. And this is really an opportunity of a memory technology that's already emerged, if you will. People already have these 3D stacked logic plus memory, as we've discussed. So again, still jogging your memory. And these exist. Maybe they're not fully 3D at the moment, but for example, in GPUs, they're connected. The logic layer is connected to the memory layer with an interposer that has high bandwidth. But through 3D actually enables you more bandwidth and lower latency. And we were looking at two key questions in 3D stacked memory. Basically, how can we change a lot in the system to accelerate an important application really fast? Make it really fast and energy efficient. And the other part was, what do we do minimally? And these are always two big questions to ask when you're doing research or development. What can I do minimally to take advantage of a new technology like 3D stacked memory? And what can I do maximally to get really the best of that technology? And we've been covering this. So I'm going to go over this a little bit more because I kind of went over this relatively quickly last time. And this is an example, right? This is an example of what you could potentially do. Remember, we had this memory and logic layer stacked together. And if you look inside, this is really partitioned into what's called vaults. These are controllers that control the stack on top of them. You can imagine that there are 64 of them, and the memory and logic are partitioned into 64 tiles, if you will. And these vaults are connected to each other with some network. In this case, it's a crossbar. And each vault consists of a DRAM controller that controls the stack on top of it. But if you want to do processing, you want to add some logic over there. So in this work, we basically added some in-order cores. In each vault, you have an in-order core. And these in-order cores can communicate with the vaults in the same, with other in-order cores that are in different vaults. Make sense? That's the idea, basically. It sounds cool, right? Now we can actually have cores. In-order means in-order processing. Why do we not have out-of-order cores? Because that probably generates a lot of heat. And one of the problems, as we've discussed in this kind of architecture, is heat has nowhere to really escape, right? Because you generate heat, and it goes up, but then there's memory layers up. It doesn't get consumed through the air. OK, so the idea is to push processing into these in-order cores. And the application we were interested in was graph processing, which is used in many, many workloads today, and it's increasingly used. So if you look at the larger system, you have these, let's say, 64 cores in 64 volts inside a single memory plus logic chip. But of course, your problems are usually larger than a single chip can contain, because this has relatively little memory. It depends on how the technology scales, of course. But your graphs are usually much, much larger. So the design has interconnected set of these memory plus logic chips. And you may have many of them, basically. There's some other interconnect. Now, the problem over here is once you connect this memory plus logic chip to this memory plus logic chip, now you go off-chip, right? So the bandwidth of these connections are much lower. So you'd like to minimize accesses to the other chips. So as you scale your problem, you will, unless you can put everything in a single chip, it's going to be difficult to overcome this bottleneck across the chips. And we will see that that's a bottleneck. OK, so how do you actually do graph processing on top of it? Basically, you partition your graph, partition the nodes of a graph across these different memories, and hopefully do a good job in partitioning such that you minimize the communication across the chips. And then, basically, whenever you want to do a computation on a node, you send the computation to where the node resides. And the in-order core that's sitting over there receives that computation in the form of messages and acts on the computation, does the computation, generates a result, and then generates some other computation such that and then sends it to where the data resides. Make sense? So this is programmed via remote function calls, which is used in distributed systems programming quite often. But we're using it on chip. And I'll give you an example of this, actually, how you transform a small portion of a graph processing workload. Remote function call is basically saying someone else, some server, to execute this function on these arguments. That's basically it. It's also called message passing. Basically, you pass a message to some other processor to execute for you. OK, so let's take a look at that. Basically, this is, again, I showed you this last time, but this is the PageRank computation that's used in many search algorithms on graphs. Basically, you're computing the rank of a node based on the weights of the adjacent nodes. So this is how it's done in a single node. But if we actually have the destination W in some other vault, essentially we'll need to send a message to that vault to do the computation. That's the idea. So how do you program this Tesseract system? You change this part of the code such that you send a message. Instead of doing this, which is assuming that you're doing this on this processor, you basically send a put message. It's just a name. For W, for node W, to be executed for node W, please execute this function for me on that W. And the function is basically this. Take the next rank of W, add to it a weight multiplied by the rank that I supply. That's the argument to the function. So you need to supply the arguments. The argument needs to be sent over there, and then this node, this volt over here, executes the function. You'll read the paper, so you can take a look at it more. OK, so basically, what you can do in this loop is you can keep sending these messages to some other nodes, assuming that you have a lot of successors in this graph. You can keep sending these messages to be executed in other nodes, and then you wait for all of those messages to be done. That's why you need this barrier over there. And then when you reach that barrier, once the messages are done, you can continue. Does that make sense? That way, you can actually generate a lot of work to be executed on some other nodes, and then you just wait for them. Of course, it's a different programming model than just a sequential model, right? You don't do it one by one, but you actually send messages to where the data resides. So w.id is really the vault ID that houses this W. So you somehow need to know that as well. So that's why the programming is a little bit harder here. OK, so this is another way of looking at it. Basically, this is the remote function call. And it's called non-blocking because when you send the remote function call to someone else, you can continue computation. Basically, you can continue with this for loop and generate another put. You can keep going. A blocking function call, on the other hand, you need to wait for the results, wait for an acknowledgement from the destination node that you send the message to so that you can make progress. In this case, there's no need to be blocking. So as a programmer, you need to know whether you need to use blocking or non-blocking function calls, right? That's the key. OK, so you basically send the function address and the arguments to the remote core. Function address is function to be executed. And the arguments, in this case, as you can see, this is the function address. These are the arguments, the value to be added, and the address of this node to the destination node. And you store the income. The remote node stores the incoming messages in its message queue. And it keeps executing over there. And then it needs to flush the message queue when the message queue is full, of course, or when a barrier is reached. So you can read the details on the paper. These are design details, actually. But essentially, it's a remote function call. Does that make sense? You send a message to the data, where the data resides. And the message consists of the function address as well as the arguments to the function. OK, so this is the messaging part. There's also some prefetching mechanism. So it turns out, if you have simple cores over here, you cannot really saturate the bandwidth that you have with these 3D stacked memories. As a result, we add prefetching mechanisms such that you can actually operate on the data earlier. But I'm not going to discuss that. If you're really interested, you can read the paper. Later, we're going to have lectures on prefetching. But one example of prefetching could be whenever you receive messages. Let's say you have a bunch of messages that are sitting over here. But the core is not fast enough to process them, or you need to access memory, so it takes time to process each of them. Maybe you just look at the messages, look at the addresses over there, and you just have a prefetcher that's called message-triggered prefetching that prefetches all of those addresses into a buffer. So that's one advantage of using this sort of message passing, if you will. You know the addresses that you're going to access over here because that's encoded in the message. You just go through this message queue and generate prefetches before the core actually gets to processing those messages. Make sense? OK. OK, I'm giving you a very broad overview because there's a lot of, this is actually a very detailed design, but it's hard to cover everything clearly. So I've given you these results, so I'm going to go through these relatively quickly. But basically, whenever you're evaluating something new, you need to compare it to the state of the art. The state of the art, one example is the DDR3-based system over here. Another example is the hybrid memory cube-based system. That's the 3D stacked memory plus logic, one example of it. And it gives you 640 gigabytes per second, much higher bandwidth because the links are much higher bandwidth. So that processors can have much higher bandwidth here. And this is a comparison point, as we discussed last time. Instead of 32 out-of-order cores, we want to also look at 512 in-order cores because we cannot put, the assumption is that we cannot put out-of-order cores over here. So we're losing some benefit of out-of-order execution, but we're getting more cores, more in-order cores, because they're simpler. So Tesseract looks like this. So the cores get exposed to 8 terabytes per second bandwidth. That's one of the benefits over here. They, of course, also have lower latency and lower energy, as we will see. And I've given you this result last time, and if you're interested in the detailed analysis, you can look at the paper. But basically, if you actually change a lot in the system and use this as an accelerator, you get a lot of benefit correspondingly. But you need to program everything again, right, as you can see. You need to change the applications to use those system calls, the remote function calls, ... And as you can see, the benefit using prefetching adds significant benefit also because it enables you to exploit that very high bandwidth that you have. In-order cores are not good at exploiting that very high bandwidth because they basically execute the instruction stream sequentially. They don't have much look ahead in the instruction stream. They cannot do out-of-order processing. So even without prefetching, you get 9x on average across 5 graph processing algorithms, which you can look at in the paper. PageRank is one of them. And with prefetching, you get almost 14x compared to the baseline DDR3 system. And if you look at, if you just increase bandwidth by using hybrid memory cube, you don't get that much over here. Okay, and one of the reasons is you can utilize much more bandwidth. And as we've discussed, it's a bandwidth-bound problem. You're basically doing a lot of processing on the data, but you don't have much computation, but you need a lot of bandwidth. Okay. So this is an interesting comparison that is in the paper. And it's not that perfect. So usually, and this is all simulation, as you can imagine, right? There's no design that exists that looks like this. It would take probably a couple of years to actually do this design. And even then, it's not clear if you actually can do it with the existing technologies because existing chips, DRAM chips, don't enable you to have this interface right now. So you need to dream as an architect. And then maybe 10 years later, somebody builds this, right? So this is an interesting analysis that you can do with simulation. It's not perfect necessarily, but for example, this is a baseline system with hybrid memory cube and many core, 512 cores. And if you actually enable, magically, 8 terabytes per second bandwidth instead of 640 megabytes per second, this is the benefit you get, about 2.3x. So you don't get 6.5x, which is really Tesseract. So the comparison point here is hybrid memory cube. That's why this is not 13.8x as the previous slide. So the benefit is not just coming from exploiting the higher bandwidth, right, clearly. And if you, OK, and you can also do this comparison over here, hybrid memory cube with many cores, and this is Tesseract with hybrid memory cube-like bandwidth. That gives you, this is the same bandwidth, and adding this model of execution, remote function calls, gets you about 3x. So the bandwidth is the same here, but then you use a different model of execution. That gets you 3x. So clearly, you're gaining some from bandwidth and some from the programming model plus all the other things that we do. And another way of looking at this is hybrid memory cube, many core with PIM bandwidth. Magically, you get 8 terabytes per second as opposed to 640 gigabytes per second. And this is Tesseract. Basically, you don't have this system, hybrid memory cube system, but you have the Tesseract system. So that gets you whatever the difference between these two are, about 3x again, which is interesting. Right? So about 2.3x of the benefit comes from getting higher bandwidth, and the rest, about 3x, comes from everything else that we do, changing the programming model, plus, yeah, everything else that's associated with it, messaging. So you can see that the accelerator design is not just about exploiting the better bandwidth, but also changing the model to really, really exploit that bandwidth. And this is even without prefetching. This doesn't have the prefetching benefits over here. OK, we can think about that a little bit. OK, so the energy, I've also shown you this result, actually, last time. Basically, energy reduction is quite high. This is, again, system-level energy, not DRAM only, entire system. So you get a very significant energy reduction compared to hybrid memory cube with out-of-order engines. So it's about 8x, which is high. OK, so this is really overhauling the entire design. And as a result, the advantage is you really specialize the system such that you have a graph processing accelerator using PIM, right? I see that as an advantage. And as a result, you get the large system and performance energy benefits, and you basically take advantage of 3D stacking for an important workload. Now, there's nothing really specific about graph processing. You can actually use the same model for some other application, right? We just didn't do it, because that requires now programming that application and porting it to this accelerator. In a sense, it's very much like a GPU today. You basically program your application such that it gets the best out of the GPU. So the disadvantage is, clearly, you change a lot in the system, right? It's not going to happen overnight, because you have a new programming model, and you need specialized cores for graph processing now. It's still in-order cores, but we have these specialization mechanisms, as you saw. As a result, it has a lot of cost, and as we've discussed, scalability is limited by the off-chip links. Right? So if you actually are communicating a lot between these different chips, you're back to square one, almost. Meaning you want to minimize the communication across these different chips. That's always a good design goal. Which means that you need to partition your graph well, or you need to have good enough locality in your graph. But this is actually a hard problem, which we're not going to get into. So the paper actually has some analysis on graph partitioning. Not very detailed, but if you do better graph partitioning, you gain more benefits, because you minimize the off-chip communication across these 3D stacked memory plus logic chips. OK. Any questions? I've covered a lot of material, actually, very quickly. But the paper is also very dense. So if you're interested, you can look at it. So I think this is actually really interesting, but this is probably longer term. For example, people can actually build maybe machine learning accelerators using this. We haven't looked at it, but that could be interesting also. And if you want to read more, this is one of the papers. It's not required, but it could be useful. OK, so let's go back to the other question. Now we've seen one extreme. And it's not clear if this is really the extreme, right? There's always this question in architecture, is this the best you can do? And I cannot answer that question, unfortunately. It would be really nice to be able to have that answer. But this goes back to the evaluation issues that we've discussed. How do you theoretically prove that your system is the best, let's say? That's very difficult to do in this case. I guess one way of doing it, just to give you an idea, is simulating your system such that everything, you don't have the memory problem. Everything hits in the cache. It's not clear if that's the best comparison point in this case, because we're changing a lot more in the system. But you really want to have an ideal. If the performance you get is exactly the same as ideal, then you achieve the best, perhaps. But then you need to define that ideal appropriately in that case. It's not a theoretical proof. It's still an empirical proof. But we didn't do that in this case, because it's a little bit difficult. But if you're interested, it's always good to think as an architect. How far away am I from the ideal, and how can I close the gap between ideal and my design? OK, let's go back to this one. So this is the second approach, again, with any technology, is what is the minimal thing that I can provide so that I can achieve as much as possible? And the other direction is basically this. The idea over here, the goal was to develop mechanisms to get the most out of near data processing or in-memory processing with minimal cost, minimal changes to the system, and no changes to the programming model. That would be nice, right? If you can get 14x this way, then you'll be golden, perhaps. But you'll see the results soon. OK, so I'll give you the key idea. So how do you do this? Basically, the idea is you have a processing in memory operation, and you encode that as an instruction. So you extend the instruction set architecture to have an instruction saying, this is my processing in memory operation. And it's cache coherent. It's virtually addressed. It's called a PIM-enabled instruction. And it operates only on a single cache block. So there's a restriction. And we will talk about why that restriction is. Well, the restriction exists because you want to ensure that coherence is not a problem. We'll talk about coherence in more detail. So this is an example of a PIM-enabled instruction. You have a PIM add. Instead of an add instruction, you have a PIM add instruction. And that's basically takes a memory address, and it adds a value to that memory address, to the value in that address. Sounds good, right? This way you can, I'll show you how you actually change the page rank code with that. There's no change to the sequential programming model, no change to virtual memory, because the processor actually decodes this instruction, does the address translation, and sends it to memory if needed. There's no change to the cache coherence. Remember, in the Tesseract case, we didn't really deal with cache coherence. We said you offload all your graph on this accelerator, and everything operates on physical addresses, and this is message passing based, right? There's no coherence over there. And in this case, there's no need for data mapping because each PIM-enabled instruction is restricted to a single memory module because it can operate at the granularity of at most a single cache block. You cannot operate on a large granularity, like row clone. Remember the row copy? You don't do that in this case. Or row bulk bitwise operations, you don't do that. You just operate on a single cache block, and you know that single cache block is in a single memory module. Right? So the mapping problem goes away. And the second idea is, where do you execute this instruction now, right? You have this instruction that the processor fetched. It says it is PIM-enabled. You could execute it in memory, or you could decide to execute it in the processor. And the idea over here is to have a simple locality predictor that says, oh, it's better to execute it here in the processor or there in memory. So if, for example, all the arguments of the instruction are in the cache, basically the cache block is in the cache, for example, then execute that in the processor. Otherwise, maybe execute it in memory, right? Of course, you can have more sophisticated predictors looking further in the program, but this is just to give you an idea of the design decisions that you may need to make in a system like this. OK, so let's take a look at this. Basically, this is, again, PageRank. It's simple. That's why you look at it. If you execute it in the processor, you basically need to bring 64 bytes into the processor and write back 64 bytes. So it's really, you're communicating 128 bytes. Whereas if you change this to a PIM-enabled instruction, which is as simple as this, basically, the programmer now needs to program this way. Or maybe compiler figures that out. Right? That's another possibility. Now, basically, that gets translated into an ISA instruction that looks like this. If it's executed in memory, basically, you send the value to main memory, and that's it. And if you have the interface to send just 8 bytes, that's great. You just need to communicate 8 bytes into main memory. So 128 bytes reduces to 8 bytes, which sounds good, right? OK, so that's the benefit. So let's take a look at, is it always good to execute in memory? And that's not a good idea. So this is empirical results again. But basically, these are some graphs, and you're doing PageRank on top of them. And these are larger graphs, and these are smaller graphs. It turns out caching is very effective for these graphs. They're in your cache. Whereas here, usually, they're in your memory. Your cache is not very effective. So if you actually do send the PIM-enabled instructions to memory over here, you gain significant performance benefit. Why? Because you reduce the memory bandwidth consumption within memory computation. Whereas you lose performance in these smaller graphs because now you increase your memory bandwidth consumption by sending it to memory, because your caching was very effective to begin with. Make sense? So that's the beauty of caching, actually. If your caches work, you want to operate out of your caches. So in-memory processing is not panacea with for everything. You really need to figure out where you should really execute your code. In this case, actually, if you think about this, if your data is already in your caches, or it can be effectively in your caches, you should really operate near that data, which is your caches, right? Not memory. OK, so this is the example of PIM-enabled instructions. Again, this is the PIM add. There's a PIM fence over here for the same reason. The processor can basically send a lot of PIM adds to memory. And the question is, should it wait for them right away? Or when should it wait for them? Right? And the programmer decides in this case, oh, it doesn't need to wait for those values until this for loop is done. This is like the barrier that we saw. As a result, it inserts this PIM fence instruction that basically says, wait until all of the previous PIM-enabled instructions return from memory. And then you can continue. That's the idea. But again, this is a programmer's decision. So this complicates the programming a little bit, or the compiling. So what are some example operations? So add is interesting, of course. It's very simple to implement. But now one of the benefits is you don't need a full processor on the memory side, right? you just need to have these specialized instruction execution units. Add is very easy to add. And these are some of the instructions that we figured out would be useful to add for different applications, as you see over here. For example, 8-byte integer increment. 8-byte integer min. You figure out the minimum of 8 integers in that case. Dot product for a support vector machine, for example. Actually, a lot of machine learning applications use dot products. So that's probably a good instruction to have on the memory side. And you can see that the input is 32 bytes here, output is 8 bytes. Again, that's a design decision, right, when you're designing the instruction set architecture. Euclidean distance turns out to be good for a stream processing application where you're really analyzing data, doing clustering on real-time data that you're receiving. And there are a bunch of others. Hash table probing, for example, hash joins in databases. So again, basically, the instructions that you need to implement on the memory side depends on the application. One good question always is, like, what is the instruction set architecture? What is the set of instructions that you should have on the other side, on the memory side, that covers a lot of applications? That's open. That's an open question at the moment. It's similar to designing an ISA. But in this case, you can actually have, well, it's actually similar to designing an ISA, right? An ISA can also have a dot product instruction. Maybe some modern ISAs don't have it, but you can add it. OK? OK, so basically, the characteristics of PIM-enabled instructions is it's executed either in memory or in the processor, so you have a dynamic decision. And how do you do that decision is important. I'll give you examples of it. Not how you do that decision, but what's the benefit of it. And it's cache coherent, virtually addressed, single cache block only. So you don't have the virtual memory problem because it's translated before it goes to memory, right, on the processor side. And the execution is atomic between different PEIs, PIM-enabled instructions. So when the memory receives them, it finishes one add instruction, and then it moves to the other add instruction, and then it moves to the other add instruction, right? But it's not atomic with normal instructions. Basically, here, it's not a blocking thing. You basically you can keep going and executing, and you need to wait for the fence to ensure that the execution of all of the PIM operations are done. Of course, these are all design choices. You could design, for example, a blocking PIM add instruction as well, right? Well, blocking PIM add instruction is essentially maybe you have PIM add, and then you put the P fence right after that. You need to ensure that it's done, right? So this is very similar to the memory fences that we have today. OK. So the key to practicality, one of the keys to practicality, other than having instructions, having PIM operations encoded as instructions in the ISA, is the single cache block restriction. Each PIM-enabled instruction can access at most one last level cache block. And actually, today, similar restrictions exist in atomic instructions. So if you want to do an atomic update to a cache block, it's really at the cache block level. You cannot do atomic update to multiple cache blocks today, because of the same reason, because it complicates cache coherence. It complicates virtual memory translation, because you need to translate two addresses now, two cache block addresses, because they may actually map to different virtual memory pages. And for cache coherence, you need to ensure that both of them are in the cache when you operate them, and no one else invalidates it. No one else reads it while you're updating one. Right? So having a single cache block is nice because you can lock that cache block and operate on it wherever you want to operate. So basically, there are other benefits, of course, which I mentioned. Each PIM-enabled instruction is only in one memory module now. Data mapping problem goes away. And yeah, I discussed this. And this also simplifies locality monitoring. It's easier to say, oh, this cache block is likely to be in the cache, as opposed to these 10 different cache blocks that I'm going to operate on are going to be in the cache. Right? OK. So let's take a look at an example microarchitecture to execute this. This is, again, not a final thing, but an example one. Basically, you have an out-of-order core. You get a PIM-enabled instruction. And if it's, you basically check using this locality monitor. The question is, where should you execute this instruction? If this locality monitor, a prediction mechanism, says, execute it in the processor because it's in the cache, then you execute it in the PIM computation unit, just like another PEI computation unit, just like an adder, for example, inside the machine. You could actually execute it on the same adder. But if this locality monitor says, oh, you don't have good locality, so execute it, send it to main memory, then the first thing you do is basically lock that cache line, saying that, oh, I'm going to execute I'm going to execute an operation on this cache line. It's going to stay in memory So make sure that I don't fetch it into anybody's cache, not this processor or the other processor. So that's a minimal change that you need to make to the cache coherence protocol, because you need to ensure that no one else fetches it, right? Somehow. Yes.
So is it like making it a dirty block?
Not really dirty block, because it's not really dirty, right? It's basically you're locking it in the cache. You have a bit saying, I'm locking it, no one else should access it. We'll talk more about cache coherence. We'll go into the details. But that's essentially it. If you think about locking, you're locking a cache block in hardware. Because you don't want to have it in the cache also. You really want, because you're not going to fetch it into the cache. It's really over here. That's right. So you need to flush it in that case. That's right, yes. If it's already in the cache, you need to somehow flush it. But maybe your prediction is wrong. Maybe you should really execute it in the cache in that case, right? That's a good point. OK. So you basically get the permission to execute in main memory. And then after that, you send the instruction to the appropriate DRAM controller. And you have these computation units over here, not necessarily cores, but functional units that can execute the instructions that we've discussed. And that gets executed over here. And then you get an acknowledgement back after some point. Make sense? Again, this is an example microarchitecture. But the nice thing about here is this is simpler, hopefully. It's not a full core. You're not sending functions. You're sending simple instructions. And still, the processor is essentially a master, right? It's really sending the instructions and waiting for them. So it's not as full-blown as what we've discussed earlier. But it's probably a step toward that full-blown thing. OK, so let's take a look at some examples. Again, these are some workloads that we've examined. We've examined some different input sets. This is just an average. So the average, as you can see, is not 13.8x. It's about 47% with large input data sets, which is probably not bad, but it's not 13.8x also. And with small input data sets, you still gain. And the energy reduction is 25% in a single node with large input data sets, again. Large input data is basically you don't fit into your caches that much. Again, 25% is not like 8x, right, that I've shown you. But it's a step toward that 8x. OK, so let me give you a little bit more on these, just to make a point. I mean, you can read the paper for these for these examples. And the paper has analysis of these applications, actually. Let's see. So let's look at the data set, effect of the data set, because this is really important when you do evaluations. These are different workloads. This is geometric mean, and this is a performance improvement, performance delta over the baseline. Baseline is executing everything in the processor. This PIM only is executing all of the PIM-enabled instructions in main memory. So that seems like it's doing pretty well here, right? PIM only. It's gaining you about 45%. But if you do locality aware, basically, if you have a decision mechanism, whenever you're in the cache, whenever you predict that it's better to execute in the processor, execute in the processor, otherwise execute in memory, you gain a little bit more. Not always. Sometimes your prediction mechanism actually loses performance compared to always executing in memory. But most of the time, you gain more. So your geometric mean performance improvement is about 47%. So the decision mechanism helps you here. But decision mechanism is, I'm going to skip this. You can look at the, well, I guess maybe I won't skip it. But one of the benefits you're gaining is the reduced off-chip transfer. This is host only when you're executing on the processor. If you're executing in memory, you're basically reducing the data transfer by about 40% over here, and a lot in many of the workloads over here. And you can read the paper for what's going on with that one. OK, so where the decision mechanism becomes beneficial is small inputs. Actually, it's really medium inputs. We'll get to there. But even small inputs, it's good. So if you have a data set that mostly fits in your caches, small input doesn't mean it fits in your caches, but it's likely that your caches can absorb them better. You get good locality because your working set fits. If you send the data, send all of the PIM-enabled instructions to main memory, you lose performance, as you can see. And in some applications, you lose a lot of performance, 50% performance losses, like 2x. But if you actually have a decision mechanism that says, oh, I predict where to execute, and based on that, I execute in the appropriate place, With the small inputs, you don't lose performance for these cases. And in this case, you gain some performance. It turns out this is not small enough, or you get random accesses in this case. So you basically are the same, almost the same as executing in the CPU, which is you recover the benefits, if you will, or recover the loss. But where the decision, and as you can see, if you have small inputs and if you send the data to be, send all of the PIM-enabled instructions to be executed on the memory side, you actually increase the memory traffic quite a bit. Because your caching is very effective, right? Just bring it into the cache once and just operate on it, as opposed to going to memory every time. That's the benefit of caching. OK, this is where you get actually the most benefit, as you can see here, with the decision mechanism. This is medium-sized inputs. Maybe they fit into, it's unlikely that they fit into cache, but a lot of it fits into the cache, maybe. And as you can see over here, if you execute these operations always on the memory side, you don't get much benefit here. You get quite a bit of benefit here. That's good. You lose some performance here. But if you actually have a decision mechanism, you get a lot of benefit. Well, your decision mechanism is not perfect here, as you can see. But on average, you actually gain much more benefit, as opposed to executing either on the processor or on the memory. So it's important to have this decision mechanism. And this is not the best decision mechanism, obviously, right? You're making mistakes, as you can see. So having these decision mechanisms is important. And it's not clear if we have the best decision mechanisms at the moment yet. And again, pulling back, this is just an accelerator, right? We have the same problem with other accelerators also. Where do you execute code is a problem, and with GPUs, for example, as well. OK, just a little bit more on evaluation. Again, energy. What happens to energy with small input sets? Well, so this is the locality where we should look at this, because we've seen that if you don't make the decision dynamically, you actually lose a lot of energy over here. But you gain just a little energy with small input sets. So you don't really gain benefits much from this architecture if your input is small. If your input becomes bigger, you gain more benefit. If your input is really large, then you gain a lot of benefit, 25% reduction in node energy, which is not bad. OK, let's look at the advantages and disadvantages of this also. I'm not going to do this with all of the ideas that I'm going to cover in this talk, in this lecture, but you should always be thinking about advantages and disadvantages of any mechanism that's thrown at you. So this is simple and low cost, right? This doesn't change a whole lot in the system. I don't know if it's the simplest. Again, I cannot theoretically prove that this is the simplest. It'd be nice. But it's simple. And no changes to the programming model and virtual memory. So some compiler can actually translate an application relatively easily, hopefully. But somebody needs to write that compiler. And you can dynamically decide where to execute an instruction. That's an advantage that we didn't have in Tesseract, for example. We offloaded everything to Tesseract. We didn't have the decision of, oh, maybe sometimes you execute something in the CPU. Right? So disadvantages, of course, as you saw, is it doesn't take full advantage of the potential of PIM, obviously, processing in memory, because we're doing as little as possible, by definition, almost. And single cache block restriction is especially limiting. Because you cannot do operations on 1 megabyte memory. So if you want to actually do a search on 1 megabyte of memory, you cannot do that with this. You need to do actually 64-byte instructions that operate on 64 bytes. So assuming that you have 1 megabyte and the instruction operates on 64 bytes, you need a lot of dynamic instructions to do that search. Right? And those all get shipped. As a result, you don't get the full advantage. OK. And if you're interested, you can read the paper for this as well. Any questions? Now I've given you the two extremes. Is this interesting? Yeah. So I think that this is actually a general approach for other accelerators as well. It's good to think about, can you actually do this with other accelerators? Can you offload an instruction to, I don't know, an on-chip GPU, for example, and take the best advantage of it? And that might be interesting. Yes?
If I do the processing in memory, the two memory rows, do they have to be in the same memory bank? Or can they be anywhere in my main memory?
So you're talking, not this idea, right?
I mean the whole concept. Or
yeah.
When I want to add two rows in my main memory.
OK, so I think you're really thinking about the, oh yeah, I guess in two concepts, sure. But it really depends. It really depends on how you're doing it, right? So for example, you're doing something like row-level operations. The biggest efficiency is if the two rows are actually in the same subarray, right?
Yeah, but for example, if I do BFS, large graph, it's almost a random access. So those will probably not be in the same row or adjacent row.
That's right, exactly. If it's in the same module, you gain benefit. Now, if they're in different modules, you have a lot more communication.
But is there still a benefit over caching or getting both values into the register?
Again, the answer, it really depends. The answer is it really depends. It depends on whether it's cacheable. You actually have benefit. If you're really doing random, so if you're really doing random access, if your caching is not beneficial, then I can almost confidently say that it's better to do it in the memory side, assuming they reside in the same memory module.
But for best performance, it would still need some locality, at least
in a memory module level. That's right, exactly. Exactly. You still need locality on that side, basically. If they're in completely different memory modules, you'll need to move data. So the idea is to minimize the data movement in the end. But you're asking good questions, basically. How, like, where should I execute? But that's why it's important to have some layer, maybe, that prevents the programmer from trying to decide this. Right? If there's a runtime decision and scheduling mechanism that says, you should, at this point, execute this operation in memory, otherwise execute in the processor using the caches. That would alleviate a lot of programming issues. Any other questions on this? Sounds exciting, right? Cool. OK, so we'll go over a couple of other things in processing in memory, and then we'll take a break. And then we'll switch gears. So I'm going to go through relatively quickly some of these things. But you can do processing in memory in GPUs. For example, a GPU, you can have a very powerful GPU augmented with smaller GPUs in 3D stacked memory. That could be useful if you're actually memory bandwidth bound. I'm not going to go into the detail of this. But similar issues exist in systems like this. For example, which operations should be executed on the logic layer? How do you figure that out? How do you ship that? So this paper provides a compiler-based mechanism to automatically do that transparently to the programmer. Those mechanisms are usually useful. And how do you, again, the problem you mentioned over here, basically, if one data piece is here, one data piece is here, and if you want to add them, well, that's maybe it's better to just do it in the main GPU, bring both of the data pieces, right? So ideally, you would like to map the data pieces in the same memory stack so that you get the best out of it. But data mapping turns out to be not an easy problem. This paper proposes an empirical approach based on an observation that you can actually map the data. You can actually predict which data pieces are going to be accessed together and relatively easily map the data over here. But that's very application-oriented, if you will. If your application doesn't have that behavior, you cannot exploit that. But a lot of these, so this is very similar to other accelerators also. And GPUs, for example, whenever you offload some code to a GPU, you really need to take advantage of the behavior of your application to do your data mapping. So it's very similar here. OK, you can read some of these other papers. I'll cover this relatively quickly also. And we'll take a break in about 10 minutes. But let me cover this, because it's actually interesting. And it takes advantage of the latency benefits of 3D stacked memory so that you can execute linked data structures faster, and propose a specialized accelerator design inside the logic layer. So let me give you the very quick summary. Pointer chasing is an important workload. It exists in many, many places. And there are challenges in it if you want to accelerate it inside main memory. And we'll cover that relatively quickly. Basically, the design is an in-memory pointer chasing accelerator. It's a specialized accelerator. And if your logic layer is reconfigurable logic like an FPGA, perhaps you can put this accelerator inside your logic layer and then take advantage of it. And I'll give you the ideas very quick. But one of the interesting things over here is you want to put a page table in that accelerator such that that accelerator actually can do virtual address translation, right? So that you can access a large part of memory. So this solves the virtual memory problem, but maybe there are other solutions also. And the key result is basically you get significant speed up for pointer chasing operations like hash tables, B trees, B plus trees, and linked lists. linked lists tend to be the most latency sensitive, right? Because to access the next node, you need the previous node's address. And you can get significant throughput improvement in databases. And energy consumption reduced a lot. OK. So basically, these are where linked data structures are important, as you can imagine. And these are building blocks for many things, right? Hash tables, for example, are commonly used in databases and other applications. Actually, genomics uses hash tables quite a bit. There are many genomics workloads that use hash tables very, very heavily. And you can imagine why, right? You're really comparing sequences, and you're hashing the sequence such that you can compare it to some other hashed sequence. OK, so the linked data structures are connected by pointers, and you need to chase pointers to find something that you're looking for. For example, if you're trying to find A, today you need to send the address to memory, you need to get the data, and then you need to send the next address after you read it, and you need to get the data, and then you need to send the next address, and then you need to get the data, and you do the comparison, of course, also in the middle. And eventually you reach. So there are a lot of round trips that you have over here. And each of them is latency critical because you cannot start the next access before you know the previous address, right? So this is one of the actually hardest problems that you have in architecture. How do you speed up these serial code? And processing in memory can help. So one of the things is serialize an irregular access pattern. So it's relatively random access. And it turns out in important applications, the time it takes to do this traversing linked data structures consumes a lot more cycles per instruction than other parts of the application. So 6x cycles per instruction compared to the other parts of the application. That's because there is a lot of latency involved in this, especially if the data doesn't fit in your caches, right? If all of your linked data structure is in your caches, then you're doing this round-trip linked data structure traversals within the chip, and that's OK, perhaps, maybe. Maybe you still want to do it, have an accelerator close to your cache in that case. That saves some on-chip latency. But if your data doesn't fit into your caches, if your access patterns are relatively random, you cannot predict what you're going to access next, then all of the memory latency plus the on-chip latency gets exposed to every single access. Right? OK, so basically, this was the idea. And as we've discussed, I've given you a previous picture already that looks like this. You basically send a find operation to the logic layer, and the logic layer does the computation and sends the data back to the CPU. So how do you enable that? I mean, you can imagine how to enable that. But basically, you need to be able to do this traversal completely inside the logic layer over here. Well, there's a couple of things. If you actually have a CPU core versus an in-memory accelerator, the benefit you're gaining is really the memory access latency, right? So let's say this is your traversal, linked data. Let's say one iteration of your linked data traversal. It takes this much time. You reduce that. So for one operation, you get reduced latency. That's one of the benefits. But the problem is if you have many, many of these traversal, let's say you design a database engine, and you're doing many traversals at the same time. If you have multiple CPU cores, you can overlap the memory accesses. It's memory level parallelism, right? Or multiple CPU threads. But if you have an in-memory accelerator that doesn't support parallelism, you would lose performance, right? So you need to be careful in designing your accelerator. And this is true for any accelerator, actually. It's always good to think about. You have a lot of parallelism on the CPU side, threads, cores, and you can exploit that. But if your accelerator doesn't support that, shipping that thing that you could otherwise execute on the cores to the accelerator doesn't buy you performance. In fact, you lose performance. So you really need to design your accelerator such that it's not slow, because it's a shared resource, as you can see over here. OK, so the opportunity in this case to design is you have a bunch of memory access. So why don't we overlap many, many computations? Basically, we see a lot of linked data structure traversals and overlap them. That's the idea. So if you look at the CPU cores, you get these two different traversals. So the accelerator has an address engine and an access engine. And address engine receives the linked data structure traversals and starts the memory accesses, and can start a memory access every cycle, let's say. It receives them. And then you can start the memory accesses right after that. As a result, you can parallelize these memory accesses. And each memory access is much faster than the CPU because you're doing it close to the memory. You're bypassing all of that latency. So that's the basic idea. That's very simple. Actually, if you had taken my digital circuits course, you will remember that this is very similar to decoupled access and execute. If you remember that the idea over there was decoupling the memory access unit from the execution unit, such that execution units can generate addresses, and then that memory access can continue, whereas the execution unit can do executions that are independent. That's what's happening over here. You can think of this as the execution unit, if you will. This can generate addresses, do a lot of independent address generations, whereas this access engine does the memory access in parallel. It doesn't need to wait. Does that make sense? So if you want to learn about decoupled access execute, you should really look at the lecture over there. I'm not going to hold you responsible for it, but it's important to see it. OK, so the basic idea is very simple, actually. You decouple the address generation from memory access. You can receive different traversals, and you can pipeline the address generation, and you can pipeline the memory accesses, and these two units operate mostly in parallel. And that enables you to parallelize the accesses that are coming from the CPU cores, as you can see. As opposed to doing this in the CPU cores, you can actually do this in memory, because each memory access is faster now. You still gain performance improvement. OK, and you can read the paper for more details. So this is an illustration of how this operates. Basically, you need an accelerator design that supports this clearly. And there's a cache over there. So it turns out this is one of the learnings that we have had a lot, and other people have also had. Or maybe they didn't, but this is what we had. Basically, it turns out there's some locality here such that you can exploit. Even if you're doing operations inside memory, it's better to have a cache inside the logic layer, because that cache is much faster than accessing memory. Right? Because DRAM access is still a lot slower than accessing an SRAM cache, a small SRAM cache that's inside the logic layer. So it's better to have a cache over here and operate out of that cache. So this access engine, for example, it doesn't always go to the memory controller. It first checks this cache. If the data is in the cache, it returns it immediately. Right? So that's the power of locality. I like calling it the power of locality. Even if you're operating maybe inside is too strong, but in the logic layer right next to DRAM, the locality is so strong that you might want to have a cache over there. And the paper analyzes that, so you can look at the paper. But basically, let me illustrate what's happening. So the CPU sends requests. Let's say traversal request 1. That goes to the address engine, generates an address, and that sends the address to the access engine, and the access engine starts the access, either to the memory controller or to the cache. And the next traversal is pipeline, basically. It goes this way. So you basically have a pipeline traversals coming into the accelerator. That way you get very high throughput from your accelerator, and you gain because memory access latency is much faster. Yeah. OK, and then everything is pipeline, basically. OK, so let's look at the other challenge. And this is actually a challenge in many, many accelerators. Whenever you have a CPU and you're offloading something to the accelerator, and if you actually generate memory addresses in the accelerator, you have an address translation challenge. In this case, it's very exacerbated, because what you're doing is really generating a pointer, a virtual pointer with a virtual address that gets translated using a TLB. And you do a page table walk. And this is one example page table. This is x86. And to be able to do that page table walk, this is what you do, right? You go through memory many times. OK, and then that gets translated to a physical address. So that's what the CPU does when it actually needs to traverse a pointer. Right? But the problem is, if you're on the memory side, and if you want to traverse a data structure, there's no TLB, no memory management unit. You have a virtual address in your hand, but you don't know what to do with it. One option is, of course, going back to the CPU and asking, CPU, please translate it for me. Now that gets rid of all of the benefits that you have, right? It makes no sense. That's why the previous work that we've discussed had a single instruction, for example, PIM-enabled instruction that basically sidesteps this problem. You do only one cache block, and that's already translated. Tesseract sidesteps this problem by saying, OK, I don't have virtual addresses. Everything is physically addressed. Right? Yes?
Is it possible to actually modify the data structure so basically that every node doesn't have the pointer to the next one, but rather have the pointer to the next few. So we can actually access few few nodes in advance, even though we might not need them. But if we expect to have like a long traversal, it might be beneficial, because then we're gonna start. There's gonna be a fully pipelined data coming to the CPU, and like we can check every time if there's something, and only wait for the the throughput of the. That we won't have to wait for the latency and then issue a next instruction, wait for the latency. It's just going to be like a throughput.
So you're not solving the address translation problem, right?
No. Address translation is still done in CPU. CPU
yes,
is still
sure.
sending
the
virtual addresses, but sending in bulk. It's
I see.
A linked list, but not to the next, but to the next few.
Okay, how do you know the next few addresses?
I don't know, indexing or something like.
Yeah, you basically need to redesign your data structure.
Yeah.
Then it doesn't look like a linked list.
Pretty much, yeah.
So I agree with you. If you actually can get rid of your data structure from having this pointer-based traversal, that's usually better. But that requires, I think, redesigning your data structure.
Sure. Yeah. But it could actually give a benefit.
Yeah, sure. It basically reduces your dependence on the previous node, right? Because you can generate those addresses much earlier. Okay. But it's difficult to do if your data structure is only a B+ tree, let's say. How do you know what are the next nodes? You need to have mechanisms, for example, to remember. That's one way of doing it. Maybe you don't redesign your data structure, but you remember which things are close by.
Or periodically, like run some indexing and have some.
Yeah, you could potentially do that. That's right. That actually, either you need to redesign your data structure or complicate the runtime system such that you do that. Yeah, a lot of people tried a lot of tricks actually with these data structures. That's why it's not an easy problem. I like the way you're thinking. Like, do you know about skip lists, for example?
Yeah.
Yeah, skip list is one way of actually trying to get rid of all of this overhead of data structure traversal, right? Instead of going to the next node, you have actually pointers to n next node. And if you know that you don't have the data over here, just jump to the next n next node, right? That's one simple way, simple example. But it's not the idea you have. Okay. So going back to this problem, there's no TLB or memory management unit on the memory side. And if you want to duplicate the entire memory management unit, it's costly. And also creates some compatibility issue. Because now if you actually have a page table over here, well, which ISA do you design it for? Page table is really a property of the ISA, right? x86 is a different page table than Spark, than Alpha, than MIPS, ... ARM. So you don't want to fix a page table design over here. So this is actually a complicated problem. It's not that easy. Okay. So the idea in this case is to decouple the page table of MPICA, meaning the pointer chasing, completely from the CPU. The idea is in the virtual address space today, virtual addresses can go to many, many places. We basically kind of color. We allocate a part that's really the part that's dedicated to this accelerator. And if you want to have pointers, you should put your pointers here. Basically, you can only allocate your data structure from this MPICA region in the virtual address space. And you map the linked data structure to that MPICA region, and that's a partial to any mapping. You can read the paper for more detail. And that way, the accelerator needs to track only this region. Make sense? So the accelerator doesn't need to track the entire virtual address space. Okay, so you can read the paper for more detail. Basically, you can optimize this so that your TLB is small, and as you can see, you can make things simpler. So there's a tiny region table that's always in the cache, in MPICA cache. So that's one of the other reasons why to have a cache, so they can cache the translations inside the accelerator. Okay. Okay, so this is also simulated, because again, this doesn't exist, right? If you want to design something like this, you may want to wait for 2 years. But then if you're really exploring the space, 2 years is not good. And you can actually, if you're interested in something like this, you can download the code and look at it yourself, or maybe build on it and do some other thing. But whenever you're evaluating performance, it's always good to look at micro benchmarks. So you can easily write a linked list micro benchmark and execute it and look at the speed. This is baseline with extra 128 kilobyte L2 cache, because it turns out the MPICA area is similar to that 128 kilobyte L2. So a good comparison point might be, what is the benefit that an extra 128 kilobyte L2 cache buys you, which is very little in this case, as you can see, maybe 2% a year. And versus what is the benefit that MPICA buys you that's similar to the area of an 128 kilobyte L2 cache. So it turns out linked list, it's very latency bound, as I said. So you get 90% performance improvement. Hash table, again, this really depends on your access patterns of the hash table. So this is one example. It's 30%, and B3, it's 20%, which is not bad for these workloads. These are actually hard workloads to speed up. And if you look at the paper, you can see the database performance benefits. So database actually gets benefit from the caching, additional caches. But it turns out in Pickup provides you better throughput and better latency also. OK, I'm going to go through these relatively quickly. And energy improves as expected, right? Because you're not moving data as much again. So linked list, that's where the energy improves most. This is the entire database application. Again, in the system energy reduces by 6%. Again, system energy is hard to reduce. 6% is not bad. OK, and there's some analysis in the paper that shows whenever you're designing something like this, it's always good to do this kind of analysis as well. Like, what is the overhead that you have in this accelerator? Should I have put a simple in-order CPU over there? And it turns out it's much smaller than a simple in-order CPU. But it still comes at a cost, as you can see. The power overhead could be significant. It's about 6% in the system. Yeah, OK. OK, you can read this paper if you're interested in this. So this is a good place to actually take a break. And I'll give you an 8-minute break today, increasing by, oh, I should have done 7 minutes because that would have put us to 2:30, but 8 minutes is good. And then we'll come back and wrap up processing in memory. I don't want to touch this. So we're done with accelerating pointer chasing. So you can imagine now, so this, I discussed this because this has a lot of interest. It covers a lot of interesting issues. One is, how do you design a specialized accelerator, being perhaps the least interesting issue. But how do you solve some of these problems related to designing a specialized accelerator? The parallelism that you need to keep up with coming from the cores, and the virtual memory, which is probably a harder problem. And also, it's also always good to keep in mind, what do you have in this logic layer? Because you don't want to probably design 10 different accelerators in the logic layer. If you have a reconfigurable logic in the logic layer for 3D stacked memory, then you can take advantage of that reconfigurable logic much better, either with specialized accelerators or PIM-enabled instructions. So having something flexible on the memory side actually helps a lot. And since these decisions are being made right now, it's good to do the research to actually figure out how things will look like in 10 years from now or 5 years from now, right? There are a bunch of other issues over here, but let's move on. OK, so these are some papers that you can look at. So one of the issues is cache coherence. I'm not going to cover this again. When we talk about cache coherence, this will become much more interesting. But if you want to partition code between the core and memory, and if you don't want to do it at an instruction level, you want to do it at coarser granularity, you run into cache coherence problems. So you say this part of the program should really get executed in memory. OK, you said that. Now, when you ship it to the memory side, what if it accesses something that's already in the caches, right? You need to provide some support such that this gets the correct data and the program doesn't produce the wrong outcome. And this turns out to be a hard problem. Cache coherence is not an easy problem in general. But now, you're shipping some code to execute over there without communicating with the CPU. But if you need cache coherence, you need to communicate with the CPU. It's similar to the virtual memory problem, but in a different way. You don't want to communicate with the CPU, or you want to minimize that communication. And this paper proposed a mechanism that minimizes that communication. And I'm not going to go through this. But it turns out, I'll give you, you can read the paper if you have interest. But it turns out the traditional, so these are some applications, interesting graph processing workloads and in-memory databases, hybrid transaction analytical databases. And the speed up that you get by shipping code with some partitioning that programmer, my student, did. These are the benefits that you get with traditional coherence mechanisms. So fine-grained coherence is like MESI coherence, which we will discuss later. You basically get very little benefit in terms of performance. If you do other types of coherence mechanisms, you actually lose performance by shipping code to the memory side. So if you have this collaboration between processor and memory, maybe it's better not to ship code to memory side if you're not going to provide good coherence mechanisms. So traditional coherence doesn't actually doesn't actually exploit the advantages of processing in memory because you have too much communication to keep the caches coherent, to keep the data coherent. Whereas ideal PIM, if you don't have any coherence over it, this is one ideal simulation that you can do. You can say magically, I'm going to ensure that there is coherence with 0 overhead. There's 50% performance benefit by offloading these applications to the memory side, which is not bad again. It's not 13.8x, but this is not specialized for each application. These are different applications, and you offload code. So if you have a good coherence mechanism, ideally you should get close to that. And the key question is, how do you get close to that with little complexity? And I don't have the answer, but you can take a look at the paper for one idea. OK. So that gives you an idea of the difficulties. And we've discussed this coherence problem in the last lecture, but this is actually one of the more difficult problems, in my opinion, to enable something to be very general purpose. Remember, Tesseract, the 3D stack graph processing accelerator that we've discussed, sidestepped this problem also, right? It said message passing, there is no coherence. It's the programmer's job to ensure that. PIM-enabled instructions ensured that that coherence problem didn't happen. It just modified. You can lock the cache block that you're operating on. But if you're actually offloading a significant chunk of code, you need to do this or do something in coherence. So, of course, there's also the question on how do you design the memory data structures so that you can operate better in memory. So this is along the lines of what you've discussed, perhaps. I was thinking that's what you were thinking, but maybe that's not what you were thinking. So if you have data structures in memory, should it be the same as the data structures that you have in the CPU? Or can you specialize it to the structures of memory, for example? I'm not going to, again, give you the paper. It's just too much to talk about here. But this is also a good question to ask. Once you are executing in memory, what should your data structures look like, right? OK, and then there's also simulation infrastructures for processing in memory, and we've discussed the emulator. You can extend things like that for simulation, or you can extend things like what Hassan has, the soft memory controller for perhaps PIM processing in memory evaluation. But I discussed this over here because it's an important problem. Again, how do you evaluate these things? Simulation is one way, but can you actually evaluate it with an FPGA-based infrastructure? That remains to be seen. And that actually concludes the processing in memory part. Basically, we're really searching for energy efficiency and low latency by doing more data-centric or computing in memory. Right? OK, I'll conclude with this slide because whenever you have a new technology, it's always good to solve the barriers to adoption. And there are a bunch of barriers to adoption because you're really changing the paradigm of execution. Right? Once you try to change the paradigm of execution, it's always good to provide a path because you can only change the world if you understand the world and help it get to the place you want it to get to. If you just say, oh, this is my good idea, and get to it somehow, maybe it will never work, right? That's never a good thing. Whenever you're doing research or a startup, right? You can have the most brilliant idea in a startup. If you don't help other people to adopt the idea, then you have a problem. You'll never make money. So there are a bunch of barriers to adoption in this case, especially because you're really changing the paradigm. So one barrier is figuring out the functionality and figuring out what applications would benefit from PIM. Maybe this is the easier one. Ease of programming is always a problem when you're actually changing a paradigm. How do you provide the interfaces and the compiler and hardware support to minimize the burden that you have on the programmer? And as we've seen, PIM-enabled instruction was an effort toward that, right? But there's more to be done. System support, we've been discussing this. That helps people to adopt the idea much more easily. Ideally, if you change things minimally, that helps people to adopt the idea more easily. And we've discussed this also. This is just a summary in a sense. Runtime systems for adaptively figuring out where to execute what, where to map the data, and accessing sharing control. This is similar to what we've discussed in MPICA, right? What if you have multiple cores requesting things to be executed from the accelerator memory? How do you provide quality of service to those cores? So these are very practical issues, but these are necessary to be solved almost to take advantage of this at the large scale. And also, of course, this is very important. How do people figure out what benefit they would get from something like this, right? So you need infrastructures to assess the benefits and feasibility of these mechanisms. So this is just a summary slide to show you that it's not easy. But it's all research. This research is being done and will continue to be done to enable something like this. But again, it's always good to think about this is perhaps the ideal thing that you can have by changing the paradigm. But you can achieve that ideal by taking step by step. Right? So those steps enable better adoption. It's always good to have that path. Okay, any questions on processing in memory? I don't intend to return to processing in memory again in the lectures, unless something really cool comes up. No? It's a cool concept? Okay, cool. Yeah. Now let's switch gears and talk about emerging memory technologies. I briefly alluded to these in processing in memory lectures and also earlier when we talked about main memory. Is a potential solution direction to fix the issues we're having with DRAM, right? I'm going to remind you of some of those. This I've already shown you, right? One of the limits of charge memory is basically it's difficult to place and control charge, and we've seen the row hammer problem. We've seen the retention problems in DRAM. We didn't talk much about it, but flash memory is also based on charge, and it has similar problems. Unless the technology provides some solution at the device level, it's going to be very difficult to scale these technologies. And it turns out DRAM scaling is already getting very difficult, as we've discussed. So how do we solve the problem? We've been examining this solution, right, new memory architectures. It's not just a solution to the scaling problem. It's a solution to the memory problem in general. But we've been looking at a bunch of things over here, more memory-centric system designs, new architectures, new interface, new functions. PIM is all about that, basically, enabling computation close to data. But we've also looked at reducing energy, reducing latency, enabling reliability. We didn't talk as much about bandwidth and reducing waste, but you can imagine things over there. We cannot talk about everything, unfortunately. Otherwise, we would have, I don't know, 2 semesters worth of lectures here. OK, and we've covered some things. But let's look at the second solution direction now, which is, oh, can we replace this technology with something else that's much better? Hopefully better. We'll see. And resistive memory technologies provide an interesting direction, interesting path, opportunity, I should say. And because they're more scalable than DRAM, and they're also non-volatile on top of that. One example is phase change memory. Basically, phase change memory, you store the data by changing the phase of material. Chalcogenide glass is one example material. And you read the data by detecting the material's resistance. I'll talk more about this in a little bit. And it's expected to scale to much smaller nanometers than DRAM is expected to scale because this scales well. And you can read the papers as to why it scales well. We're not going to go into the circuit or device theory, actually, over here. But this is a beautiful paper that I recommended earlier by Raoul from IBM, Journal of Research and Development. It's a beautiful journal, actually. It's still published, but I think it's not available online fully. It's in IEEE Explorer. So you need to pay for it. But if you're an ETH student, you can actually get it for free. But basically, that's a beautiful article that talks about the device technology itself. And they prototyped it at 20 nanometers. In 2008, DRAM was at 20 nanometers in 2017, maybe. Well, 16, 15, whatever. And this is expected to be denser than DRAM because you can store multiple bits per cell, and I'll show you an example of that. The problem is these emerging technologies, especially phase change memory, but others as well, have some shortcomings. And some of them have many shortcomings. The key question is, can we enable this scalable technology to replace, augment, or maybe even surpass DRAM? And that's a very system-level question now. Because you take this technology, you enable it. And the technology is not ready. A lot of these technologies that we're going to discuss are emerging because they're really not ready at the moment. They can be manufactured at some scale, and that scale is very small. For example, actually, phase change memory, I don't know. Maybe I shouldn't speak, because there's a product out there called 3D X-Point from Intel that's rumored to be phase change memory. It's probably phase change memory. I don't remember its size. It's not memory right now. It's not used as a replacement. It's not proposed as a replacement for main memory right now. It's proposed as a replacement for storage devices. But if it scales better, at some point, it will become potentially a replacement for main memory also. But for example, STT-MRAM, there are products out there that are of the size 64 megabits, which is not exactly a 1 gigabyte DRAM, right? So these are emerging. These are going to get there at some point. That's the hope, at least. So just to put this into perspective, flash memory was like this, like 25, 30 years ago, when people were researching flash memory. Other people were laughing at them, perhaps, saying, oh, this will never get there. But it got there, and it actually changed. I would argue that it really revolutionized a lot of the things we do in computing today, right? I don't think I'd be as happy with this phone if it didn't have flash memory in it. And I'm pretty sure that I wouldn't be as happy with this laptop if it didn't have flash memory, if it didn't have an SSD in it, right? So these technologies are not mature yet, but if they become mature, they can change things quite a bit. Okay, and we'll see what kind of things. Okay, but let's look at the technology first. So what's the difference? In charge-based memory, you write data into a cell by capturing some charge, Q, capacitor in DRAM, floating gate in the flash memory, and you read data by detecting the voltage. And that turns out to be an error-prone process when you scale the technology to very small nodes. In resistive memory, different examples, you basically write data by pulsing some current, and you read data by detecting the resistance. And this turns out to be much, much more scalable. You can do it much better. And again, read the device papers for that. But let's take a look at these different technologies very quickly. I'm not going to take sides with any technology over here, and all of them may be potentially successful. But it's good to understand the technology. For phase change memory, I'm going to cover more because I know more about it, and this is actually very, very interesting. And this is actually a really old technology because it's used in rewritable CDs that you have. And I'll talk about that in a little bit. But basically, you inject current to change the phase of some material, and different phases have different resistances. And then you can detect that resistance. In STT-MRAM, spin transfer torque magnetic memory, you inject current to change the polarity of a magnet, and then your resistance is determined by the polarity of magnet compared to a reference magnet. So it's a very different technology. But the common thing is you're determining resistance with a very different underlying technology. In memristors, RRAM, and ReRAM, there are different parameters here, but essentially you inject current to change some atomic structure, and the resistance of the cell is determined by the distance of the atoms, or the atomic structure itself. And of course, clearly, for these to work, you need to be able to reliably change the phase, change the polarity, change the atomic structure, and also reliably determine what you've done, right? The resistance of the phase, the polarity of the magnet, and the distance of the atoms, basically. You need to have a storage device to be reliable, and you need to have the access device to be reliable. So let's focus on phase change memory a little bit. This is very interesting. There's some phase change material, and there are a bunch of different phase change materials. Chalcogenide glass is one of them. And this material happens to exist in two states. Amorphous state has low optical reflexivity and high electrical resistivity, and crystalline state has high optical reflexivity and low electrical resistivity. Basically, two different states. And this is interesting because this is exactly why this has been successful in rewritable CDs, basically. You can reliably change the states between amorphous and crystalline, and reliably read the data by shining light on this material, and you get different reflexivities. As a result, you can determine which state you're in, and you can encode 1 or 0. That's the process in rewritable CDs. Now, the problem is, of course, that's a very slow process. Right? So recently, people have developed these access devices that can determine the resistance of phase change memory and do it at a very fast pace, fast speed. IBM actually has pioneered a lot of research. So if you read that IBM paper, you can read some references, but there's also other research. Actually, that's an old paper, so it probably doesn't reference the most state-of-the-art read device research. But the reason why it's interesting today as a potential replacement for main memory is because these read devices can be much faster. Okay. This is what the thing looks like. Basically, you have some chalcogenide glass over here, and then you have a heater. And by heating the material in a controlled manner, you can change the states between amorphous and crystalline. And I'm going to talk about that heating very briefly. But basically, PCM cell that looks like this can be switched between states reliably and quickly. And just like any storage device, you can control it with a word line and a bit line. Right? You can connect that storage device to a word line and a bit line. Okay. So how does it work? Basically, in order to write data, you change the phase by injecting current. To set the cell, set may be encoded to 1, and reset may be encoded to 0. You need to have sustained current to heat the cell above some crystallization temperature. This is, as you can see over here, for a sustained amount of time, you need to supply the set current. So it takes some time, and then you go into the crystallization state. Makes sense. You can read the papers in detail if you're really interested in exactly how it works, right? But that's basically the idea. You can reliably set the cell. To reset the cell, you basically need to apply a lot of heat, like 600 degrees Celsius. That's one of the downsides of this technology, actually. How do you do that heating? And how do you sustain a lot of sets, a lot of resets, if you actually need to heat the device to do that reset? But you need to apply it quickly, such that you melt the material and quench it. OK, to read, you need to detect the phase by detecting the material resistance. Again, the two different states. So people have done this. Actually, these pictures are from IBM. This is the set state, and this is the reset state, high resistance state. Basically, this part is high resistance, and people usually describe it as like a mushroom cloud over there. So you can actually see these things, which is interesting. But there's a huge difference in the resistance, as you can see. That enables the access device to operate fast. If the resistance levels were really close, then it would be difficult. In DRAM, it's actually very close. That's the problem, actually, the charge levels. Whereas here, there's a huge distance between the two states' resistances. OK, so that's all about the device. I'm not going to go into more detail in this particular device. But let's see at the high level, as an architect, what are the advantages of this. It turns out it scales better with DRAM, better than DRAM, and also flash. And it requires current, because it requires current pulses which scale linearly with feature size. And if you want to really learn more about it, read the Raoult paper from IBM, this one. And we've already discussed this, basically. The second one can be denser than DRAM. I'm going to show a picture of this very quickly. And people have prototyped it with 4 bits per cell and also 2 bits per cell. It's non-volatile, which sounds nice. You can retain data for a long time, in theory. DRAM is not non-volatile. And there's no need for refresh. You have low idle power. The refresh problem goes away. Right? Sounds nice. And this is how you can encode data. Basically, you have the cell resistance. And you basically, if you say any resistance below this value is encoded as 1. Any resistance above this value is encoded as 0. Actually, in flash memory, it's voltage over here. And if you want to have multi-level cell, basically, you can store more than 1 bit per cell. Of course, it has some drawbacks as well, because you have higher latency and energy. But now you have higher density, as you can see. Basically, you can divide the resistance range into 4 in this case. And this range stores 1, 1, 1, 0, 0, 1, 0, 0. But of course, the downside of this is now you need more precise sensing and modification of the cell contents. Right? It's not, now you have a smaller resistance range. And as a result, this leads to higher latency and energy, it turns out. So that's one trade-off between single-level cell and multi-level cell. The same trade-off exists in flash memory also. The reason you cannot do it is because you can chop up this resistance range into multiple sub-ranges. It's very difficult to do that in DRAM. You need a very, very specialized sense amplifier design, which really complicates and increases the cost. There is a cost increase over here, again, but it's more reliable. OK. Does this make sense? So this is how you can increase the density without actually changing the capacity, or without actually adding more cells. Right? That's what I meant to say, actually. Because it's the same cell stores 2 bits. If you want to store 3 bits, you divide into 8 ranges over here. OK, so let's see. So we're going to talk about the properties again. So how do you figure out the properties? And this is a problem with any emerging technology, actually. You don't know the properties because no one has manufactured it, maybe. Or maybe people have manufactured it, but you don't. They all have contradicting things. So we did this study, actually, in 2008. We basically decided it's an interesting technology, and maybe DRAM can be replaced with it. And we said, oh, let's look at the prototypes, because we didn't have a device ourselves. Actually, I don't even know how to manufacture that device. I'm not a device person. I would love to be, but that requires a lot of learning also. But basically, what we did was we went ahead and looked at all the public information, and as much as we could get our hands on, of course. And these are different papers in the field that were published, academia, industry. It's a mixture. Some of them are from Samsung, I believe Hynix, IBM, but also academic research. And these are different parameters of the technology, all phase change memory. And you can see the year, maybe not interesting, array size. So you can see the array size. Some of them are large, actually. So cell size. You can see the access device, different devices over here. You can see the read time, read current, read voltage, blah, blah. You can see these things. These things mean that that value is not reported, so you don't know about it. Maybe they didn't measure it. That's usually a problem with emerging technologies. You don't have enough information, yet you need to perhaps make decisions in the system level to enable such a technology, right? So this one is actually a nice one, right, as you can see. I think this one is from Micron, and that has a lot of data over here. But basically, the other thing is they're not all consistent with each other, right? Some of them, for example, is a reset time that's 10 nanoseconds. Some of them is a reset time that's 60 nanoseconds. So you have a lot of discrepant result. And this last thing over here is something that we're going to talk about. This is endurance. How many writes does it take to kill a cell? Meaning you cannot write to it anymore. So for example, some of the studies show 10 to the 9 writes. Some of the studies show 10 to the 4 writes. And some of these are empirical. Some of these are actually based on measurements. A lot of them are empirical. So how do you trust the data to begin with when you're embarking on actually enabling some future technology? OK, you can stare at this for a long time, but this is just to show you that it's not easy to actually even study this technology. OK, but let's abstract. As an architect, you need to actually make sense of what you're given at the lower level, even if you don't have good models. At the bigger picture, where is this? Basically, it's very close to DRAM in terms of latency. So latency is comparable to DRAM, but it's slower. 4x is what a lot of people assume. This paper assumes, which I'm going to talk about also. So it's much better than flash, as you can see over here. This is latency in terms of processor cycles for a 4 gigahertz processor that's taken from this paper. And hard drive is also much faster. So it actually is a competitor to DRAM if you think about it. Or maybe something that can augment DRAM to be more scalable. If DRAM doesn't scale to give you capacity, maybe you scale this to have a lot of capacity, but have a little bit of DRAM also. OK, so let's look at the parameters. Read latency is not as good as DRAM, much better than flash. Write latency is worse than DRAM, actually better than flash, but I don't have it here. So write bandwidth is limited because one of the reasons is the temperature, as we've discussed. You need to heat the material when you're writing, and that takes write bandwidth, but you can have solutions to that, maybe. So dynamic energy is not good, so I'm giving you a lot of reds over here. So hopefully there are some greens as well. We're going to pull back. So as you can see, the read energy is actually worse than DRAM, 2x worse, which is not that bad, but the write energy is much, much worse than DRAM. Whenever you're writing, you consume 43 times more energy than a single DRAM write. Doesn't sound that good, right? So you probably don't want to write to this memory. You want to read from it. But it's on par with NAND flash. So it's somewhere in between DRAM and NAND. Endurance, DRAM doesn't have this problem, as you can see. So the endurance problem is caused because of these high temperature writes. Basically, you induce phase change at 650 degrees Celsius. Of course, it depends on the material and technology. But the problem is if you heat up something to that high temperatures, the contacts degrade from thermal expansion and contraction. And as a result, you can do only so many writes. That's the breakdown mechanism or wear-out mechanism in phase change memory. So it's much worse than DRAM, but it's better than NAND flash. NAND flash actually has, for example, if you have a single-level cell NAND flash or multi-level cell, maybe you can do 3,000 writes to a cell. Actually, multi-level cell, 3,000 writes. If you have a 3-level cell where you can encode 3 bits per cell, that's, the endurance of NAND flash is much, much worse, actually. It's about 100 to 300 writes per cell. And these things work somehow, right? Amazing. OK, but this is not as bad, but it's much worse than DRAM. So DRAM is not supposed to have a wear-out problem, although that remains to be seen. Cell size, so this is the big advantage, basically. You don't need to worry about all of this stuff. You're going to have a reading where you read about it. But the cell size is today larger than DRAM, but it's expected to scale much, much better than DRAM. That's the expectation. And actually, people have prototyped it at a much smaller scale than DRAM. So hopefully, that expectation will be met. So let's, again, take a step back. As an architect, you need to, again, make sense out of this. So what are the pros? What are the greens over DRAM? You get better technology scaling, so hopefully you'll have much better capacity and cost. You get non-volatility, so this could be persistent. So this could replace your hard disk, SSD perhaps, as well as your main memory, maybe. And you get low idle power. The refresh problem goes away, which is good because that's the main scaling problem, as we've discussed with DRAM. The cons are, unfortunately, you get higher latencies, especially write latencies are much higher, but read latencies, which are difficult to tolerate, are higher also. Higher active energy, especially write. lower endurance, a cell dies, which you didn't have this problem with the DRAM before. And there are a bunch of reliability issues, which I'm going to ignore for the purpose of this discussion, because any memory that is scaled to very small technology nodes will have reliability problems. Yes? Should get the catch box, by the way. Okay.
Not really a computer science question, but how do you heat a single cell to 650 degrees Celsius? And then again, at the same point, if you heat all cells surrounding a single cell, shouldn't that cell be heated up as well and giving the same scaling errors?
Yeah, exactly. I think that really goes into the engineering of that heating device. So the real answer is I don't know exactly. You can read about it, and that tells you, and then I forget later on. So you should take a look at the recommendation that I provided over there. But that's you have a very good point, because the difficulty is really how do you isolate this heating across the cells, and that actually causes some of the reliability issues that you have.
So it would run to the same problems like DRAM in the end?
It could, I think, yeah, it could.
Okay, so it's not really known at the...
Exactly, that remains to be seen.
Okay.
I don't think anyone has proven whether you run to the same problems as DRAM or not yet. Okay. So that's one potential reliability issue, but there are other reliability issues like resistance drift. For example, in DRAM, you charge leaks, but here the resistance actually drifts. It doesn't stay constant. So you need to actually refresh it. But the time scale of that resistance drift tends to be much larger than the time scale at which charge leaks. So that's a good part. You refresh much less frequently, every 3 days, let's say. Much better, right? There are also other reliability issues like read disturb, write disturb. All of these things exist in PCM. And at this point, because the technology is not mature, it's not clear which ones are the really dominant reliability issues. That's one of the other problems with emerging technology. Somebody needs to solve at least some of the basic reliability issues so that you get to use it in the system and figure out what's exactly the big reliability issue, right? So DRAM and Flash have made that jump. Flash made the jump by saying, oh, controller needs to fix my reliability issues, right? But it's there. Maybe one of the solutions will be you have a controller together with this, which DRAM is going towards anyway. So the controller may fix these reliability issues. Okay, but your point is very good, because I think in the end, the scalability of this technology will probably be limited by that heating, that high temperatures. If somebody cannot reduce those high temperatures, it's not clear how scalable it will be. Okay, so we're not going to talk about reliability anymore, except for endurance. Endurance is a little bit, it's a reliability issue, but it really affects how you write to the device as well. So there are challenges in enabling phase change memory as a DRAM replacement or helper. We want to mitigate the shortcomings, the red parts, and we want to find the right way to place PCM in the system. So let's take a look at some options. This is a picture from 2008 again that we drew on the board. But basically, this is a conventional system. We thought at that time this is an intermediate step. And in the future, if PCM is really a good technology, people will build things like this. We're going to get back to this, but this is the hybrid DRAM PCM approach, which I believe is more viable today, at least with this technology, with this PCM technology. And there are a bunch of questions over here that we're going to cover later. But first, let's examine this maybe more aggressive solution, right? It's more aggressive because now you're replacing this DRAM technology with maybe not so good PCM technology. So the question is, how do you redesign the system to overcome the shortcomings of PCM? Let's take a look at that. So this paper that is your reading looks at, based on the survey that I've just discussed, derives some average parameters for PCM at a feature size of 90 nanometers. We cannot do smaller than that because the published work doesn't have consistent data at smaller nanometers. But these are the parameters that we're going to use for simulation. Again, as an architect, simulation is your field of dreams, right? You basically are going to look at PCM that has 4x the read latency and 12x the write latency of DRAM. And these are the energy values, and a cell dies after 10 to the 8 writes. Density will not be accounted for in this. We're going to assume DRAM and PCM are the same capacity. I'm going to show you later results from another paper that doesn't assume that. So this is the more pessimistic case. What if PCM doesn't provide you capacity benefits, then even then, how do you enable it? OK, so you don't need to understand all of this, but this is basically normalized performance, delay, and energy, memory energy compared to DRAM. And this is endurance. So what happens if you replace DRAM with PCM in a system that looks like this, 4 cores, 4 megabyte L2 cache? We organize a PCM exactly the same as DRAM. You can think of this as taking the current DRAM structure that you know very well after the lectures, replacing every single DRAM cell with a PCM cell with the characteristics that I showed over here, and simulating it. Now, if you simulate this, it turns out with these workloads, you get 60% performance degradation, 120% energy increase, and your memory dies after 500 hours. The lifetime of your memory is not good. Doesn't sound good, right? It sounds actually pretty bad. Actually, in all dimensions, 60% performance degradation doesn't sound good. Who can tolerate that sort of performance degradation? Probably not the cutting edge. So this doesn't sound good. So how do you actually fix the problem? So in this paper, we took a look at the PCM chips. How do you design the phase change memory chip to fix the problem? Basically, I think I'll give you the key idea. The key idea, if you have this sort of memory, you don't want to write to it. You want to do a lot of buffering to minimize the number of writes that you do. That's the unfortunate fact, because writes are really bad in terms of endurance, writes are really bad in terms of energy, writes are really bad in terms of latency, right? Everything. That's the first step. The second step is you don't want to read from it either. So you want to do really good caching. Sorry, that's a joke, of course, but you want to reduce the reads, because reads are also slow, right? And their energy is high. So it's not a good enough technology to replace DRAM perfectly. So you really want to do some system-level stuff around it. And the stuff is really caching or reorganization of the device such that you do better caching and minimizing the writes. Basically, that's what the paper does. You're going to read it. But one of the ideas is, instead of having, so one of the differences is, if you look at DRAM, remember we had this large row buffer, right? In phase change memory, because this is non-volatile, you don't need a large data row buffer. Whenever you activate a row, you can just take a single bit, because you didn't destroy the data. The reason in DRAM you have to have this large row buffer is you need to have this sense amplifier that really needs to restore the data back that you destroyed. In phase change memory, you don't need to do that, so that you can have smaller sense amplifiers. And as a result, you can use this row buffer space for other rows, or the other parts of the row that you may have read in the past. So you can reorganize your row buffers, basically. Instead of having a single large row buffer, you have multiple narrow row buffers, because this is not, the reads are not destructive. So you can take advantage of the technology to reorganize the peripheral circuitry. And if by doing this you do better caching, now you can have caching policies here, just like tiered latency DRAM, right? We've discussed briefly, but at the row buffer level over here. And as a result, you get better endurance, latency, and energy, because whenever you hit in the cache, you don't access the array over here. And the second idea is, whenever you're writing into the array, you write at a much smaller granularity, ideally a single bit. So Samsung, for example, had an experimental phase change memory chip where they would figure out which bits actually need to be rewritten, and they wrote only those bits. So if you're actually modifying, let's say your row is smaller here, 64 bits, your write granularity is 64 bits, but you changed only one bit, really. You just need to write that bit. That's it. That actually gets rid of a lot of the writes and endurance issues as well. In this case, we were at a smaller granularity, basically. OK, so that was the idea. So if you do that, things look better. With the same workloads, the performance degradation compared to DRAM is only 20%, which is not bad. The energy is on par with DRAM. Take that with a grain of salt. Energy modeling is not easy, and I'm not claiming that this is really a correct energy model. But it's better than what we had before, 2.2x. I don't expect really. But so the reason it's 1.0x is because you eliminate a lot of the idle energy. Refresh is gone. Idle energy is gone. But I'm not sure if this is really correct. And your lifetime is improved. Average lifetime is, instead of 500 hours, it's 5.6 years, which is slightly better. It's slightly better because there's no guarantee, right? OK, so scaling hopefully improves energy, endurance, and density if you're optimistic. But if you're not so optimistic and if you're cautious, worst case lifetime is much shorter because you don't have any guarantees. So you look at some applications over here. This poor application, for example, even with the optimizations that I've discussed, the endurance is much less than a year over here, as you can see. So it's not 5.6 years. So memory dies very quickly still. Doesn't look good. In fact, one of the problems with no guarantees is this is a security problem also, right? If you actually have an application that's very write-intensive, it can try to destroy your memory, right? Doesn't sound good again. And people have looked at that. The other caveat is memory-intensive applications see large performance and energy degradations. So that's probably not good also. And you can see a variation. Maybe these are not the most memory-intensive applications. And maybe we use optimistic phase change memory parameters. So this is still not clear. So the jury is still out. OK. This is your required reading, so you should take a look at that. So hopefully you'll learn about this technology at that time. And this is a longer or shorter version. OK, another version of it. OK, let's look at another different technology, which may be more interesting, but may not be either. None of these are perfect again, right? So this is STT-MRAM, spin transfer torque magnetic memory. That's one particular example of magnetic memory. Magnetic memory comes in many different devices. So in this case, you have a magnetic tunnel junction device that looks like this pictorially at the high level. You have a reference layer that has fixed magnetic orientation, and you have a free layer that's separated by a barrier from this reference layer. You can think of these as two magnets, basically. Free layer you can control the orientation of by injecting current. And the magnetic orientation of this free layer with respect to the reference layer determines the logical state of the device, basically whether you have high resistance or low resistance in this device. Basically, you can encode a logical 0 or logical 1 based on the high resistance versus low resistance, right? So if you want to write to this device, you push large current through this magnetic tunnel junction device. Again, this looks like memory, right? You have an excess transistor and a bit line. You push large current into this device to change the orientation of the free layer. And if you want to read it, you sense the current flow. So there are reading mechanisms that we're not going to go into. And you can read this paper as an example. So if you look at, again, pull back and look at the pros and cons. Pros of this technology over DRAM is similar to the pros that phase change memory has over DRAM. This didn't change. Better technology scaling, non-volatile, low idle power, no refresh. Sounds good. This is resistive again. Cons are better. Basically, this actually has similar read latency and similar read energy as DRAM, which is good. But higher write latency and write energy. Writes are still programmatic. And you don't have the endurance problem. That sounds really good, right? But the disadvantage and reliability issues I'm going to skip again. It has reliability problems just like any other emerging technology. The unfortunate thing with this technology currently is it has very poor density. So today, the density is the size of one of these cells is maybe 40 times the size of a DRAM cell. So as a result, your density is not good. So in fact, the size is on par with SRAM cells. So people are actually thinking of potentially replacing very large SRAM caches with STT-MRAM. But maybe if the technology scales well and if this problem is solved, it could potentially be a very good replacement for DRAM as well. So there's another level of freedom which exists in some of these technologies, not all of them. By reducing the size of the magnetic tunnel junction device, you can actually trade off non-volatility for lower write latency and energy. Because the device is smaller, you can push current much faster. But then it's not as non-volatile anymore. It can lose data. So it becomes more DRAM-like, if you will, which is really interesting. So the question is, can you take advantage of this trade-off as an architect, potentially, right? So let me give you some results with this, and then we're going to take a break before we move on. So we did a similar study with basically replacing every single DRAM cell with a STT-MRAM cell with some characteristics that I didn't show over here, but you can have them in the paper. So the characteristics are much better than phase change memory. And of course, you still need to architect it such that writes are buffered. Writes don't directly go into this memory. If writes directly go into this memory, your latency and energy increases significantly. So you can read the paper for buffering mechanisms. But basically, the takeaway is the performance loss compared to DRAM is not bad. As opposed to 20%, now you have within 10% performance loss, and you get significant energy savings. So again, energy, take this with a grain of salt. This may or may not be a perfect model, but the trend is that it's much better than DRAM. It's definitely much better than phase change memory. So this may be a good alternative, assuming this really poor density problem is solved somehow. OK. OK, this is a good place to take a break. Let's take another 8-minute break, and then we'll continue with hybrid memory systems. OK, let's continue. OK, given what I've described, I mean, I wasn't entirely joking when I said you don't want to write to this memory. That's definitely clear. And you want to minimize the reads from this memory also. So given that, I think a potentially much more viable approach is something that looks like this, basically a hybrid or a heterogeneous memory system. And this should not be a surprise to you. Remember the tiered latency DRAM. You had 2 different types of memory, fast and slow. No, fast and slow doesn't make sense, but fast and low capacity, or slow and high capacity. How do you get the best of both worlds? You start with high capacity and create a small region that makes the memory heterogeneous. So it's similar over here, except different technologies, but the concept is heterogeneity again. If you have 2 different technologies that are good at different things and bad at different things, why don't you combine them together to get the best of both worlds? But of course, this requires now some management, just like tiered latency DRAM required management. Right? You need to put the data that you really need to be accessed with low latency to that low latency portion. Here, you need to design the software and the hardware, and that's also a design space exploration and design decision, to manage the data allocation and movement to achieve the greens of the technologies as much as possible while avoiding the reds as much as possible. So for example, if this technology has a wear-out problem, endurance problem, maybe you do the write buffering in the DRAM. Writes actually stay as long as possible in DRAM. Hopefully, they won't destroy your locality significantly, because that may not be good. But there's a trade-off now. Maybe you keep the writes in DRAM before you actually send them to phase change memory to be written. Or maybe you keep the writes in DRAM and you never write them back to phase change memory. You write them back directly to the SSD, right, after you buffer them. So you have different design choices. That's an architect again. So this is a key problem now we're going to discuss. Basically, how do you provide the best of multiple metrics with multiple memory technologies? And in the end, this is really heterogeneous memory technology. And I think configurability and programmability will be important also, although you'll need to think a little bit abstractly when I discuss this. So there are many, many issues in a hybrid memory system. First of all, you have 2 different types of memories. Are they both parts of main memory? Are they both visible to the system software? Or is this one cache? Is one of them a cache that's managed by the hardware? Do you partition the memory address space between the 2, virtual memory address space? Or one of them is invisible to the virtual memory address space? Even that's a design decision. A lot of the things I'm going to describe will assume that DRAM is a cache to phase change memory. But it doesn't have to be that way. You could expose it to the system software also. There are, of course, other trade-offs now. If you want to move some data from one memory type to another memory type, do you really want to have the system software to be involved? Because these are very low latency memories. If the system software needs to get involved, that takes a lot of cycles. That's why a lot of people are looking at using DRAM as a cache. So granularity of data movement and management between the different technologies. So if, for example, you decide this data is important to keep in DRAM, what's the granularity? Is it 64 bytes? Is it 1 byte? Is it a huge page, 4 kilobytes? Is it even bigger? So that determines, again, your effectiveness. Who manages this memory? Hardware, software, or cooperative? There are many approaches again. When do you migrate the data from one memory to another? And when do you bypass one memory to another? There are many design decisions here also. And if this is used as a cache, how do you design a scalable and efficient large cache? Because the caches that we've been used to so far are smaller, right? Now we're talking about, let's say, 4 gigabyte DRAM, 1 gigabyte DRAM. If you manage this at a smaller granularity, let's say 4 gigabytes is 2 to the 32 bytes, right? And if your granularity of management is cache block granularity, that's 2 to the 6. Now you have 2 to the 26 tag store entries. Where do you store this? That's huge by itself, right? That's more than 1 million. That's to 32 million, 2 to the 6, 64 million entries, right? If you have a hardware store in the memory controller for a tag store, that's a lot of space. So you have a problem. And also, it's not scalable necessarily, right? If you have a tag store in the memory controller. We have the same problem with Raider, remember. If you add more memory to the system, you need to have a tag store that's scalable. OK, there are a bunch of other issues. We're not going to cover all of them, clearly, but this opens up a huge design space again. So one option is DRAM used as a cache for phase change memory. In this case, phase change memory is main memory, and DRAM caches memory rows or blocks. The benefit is you have reduced latency on a DRAM cache hit, and you can use the DRAM as a write filter. You buffer the writes. Right? And I'm going to assume that the memory controller hardware manages the DRAM cache. The benefit is this eliminates the system software overhead. You don't need to go through the operating system to actually move the data. OK, there are three issues that we're going to discuss. What data should be placed in DRAM versus kept in phase change memory? What is the granularity of data movement? I'm going to discuss that a little bit less. How do you design a low-cost hardware-managed DRAM cache? These are all design issues. And there are other issues, as we've discussed in the previous slide, which we're not going to tackle. So I'm going to give you a couple of ideas. Locality of our data placement and cheap tag stores and dynamic granularity. But before that, let's take a look at the system. And this is another paper that I recommend. I'm going to reference it later on. Basically, the goal when you have a DRAM as a cache for phase change memory, the goal is to achieve the best of both DRAM and phase change memory. And again, this could be STT-MRAM also, right? That's why it says I have /NVM over here. We would like to minimize the amount of DRAM we have in the system because it's expensive and it's not scalable without sacrificing performance and endurance. So to be able to do that, we want to use really efficiently utilize this DRAM as a cache to tolerate the latency we have to PCM and also get good write bandwidth. So one of the other issues in PCM is write bandwidth is low. So if you have a DRAM buffer over here, you actually eliminate that write bandwidth issue in addition to endurance problems and the latency problem. And PCM is provided as main memory so that you can have large capacity at good cost and power. So we're going to assume that you can design the DRAM with some tag store. And of course, there needs to be a write queue as well, because it takes really long to access that phase change memory. So this is one design. Of course, you can imagine other designs. OK, so how do you actually manage this DRAM buffer? Let's take a look at some ideas. So you want to minimize the writes, right? So one minimization could be whenever you get the pages from the disk, you don't bring them to phase change memory, but you bring them directly into the DRAM buffer. That sounds like a good idea. You never write to phase change memory, right? If you could eliminate that, that's good, right? That's what I meant by don't write to this memory. So that's a write filter, that's a lazy write, basically. Maybe you don't write back also. Maybe you have another path over here this way, right? Also, only dirty lines from DRAM page are written back. Or maybe you write the entire page over here. So that's another trade-off. Basically, these are partial writes that we've discussed earlier. And you can maybe do page bypass. For example, if you need to evict something that's not dirty, that's clean from this DRAM buffer, you just drop it. Right? You don't write it back to phase change memory, hoping that you're not going to need it again. Right? Of course, you can have a predictor for that as well. So these are three different techniques. And this paper uses these three different techniques and evaluates a system with some assumptions. So this is actually a very high-level simulation. So it's really system-level simulation. It's even less accurate than a microarchitectural simulation. But basically, you're looking at a 16-core system, 8 gigabytes DRAM, main memory with some parameters. And we're even simulating the hard disk drive with flash and a flash hit rate of 99%. That's assumed. And the assumption we have is PCM is 4x denser and 4x slower than DRAM. And we're assuming DRAM block size is the same as PCM page size, 4 kilobytes. So these are 4 different systems. The first one is 8 gigabyte DRAM. That's today, let's say. And these are some workloads. Some of these are from IBM databases. But you can see k-means clustering, for example, blah, blah. And this is the equivalent cost point phase change memory. That's the assumption. At some point, phase change memory will scale so well that the same price that you're going to buy 8 gigabytes DRAM with, you can buy 32 gigabyte phase change memory. Now, if you look at these, this is execution time, so lower is better. 32 gigabyte phase change memory actually already improves your execution time quite a bit, as you can see. Why? Because now your workloads don't need to go to flash or hard disk as much. Because you have a lot more main memory capacity. So that's the optimistic view, as I mentioned. In the previous paper, we had the pessimistic view. We didn't assume this We assume the same size DRAM and phase change memory. As a result, we got performance degradation. The optimistic view is basically PCM is 4x denser at the same price point as DRAM. So you can replace, when you're replacing 8 gigabyte DRAM, you're really getting 32 gigabyte PCM. And that actually buys you performance in these workloads. Some workloads actually lose performance, as you can see over here, because they're not limited by the size capacity, but they're limited by the latency. And that's true for this one also. OK, so but if you have 32 gigabyte DRAM, this is, let's be pessimistic again. Actually, 32 gigabyte DRAM is much better, as you can see, right? The green bar over here is much lower than the blue bar. Now, if you actually have a hybrid memory, 32 gigabyte PCM plus 1 gigabyte DRAM, because DRAM is costly, you get very close to 32 gigabyte DRAM. That's the idea. So the hybrid memory is almost the same cost as these two over here, but it gets the performance of a much more expensive memory. And yeah, and you can read the paper for more detail. So this is still pessimistic. Again, the jury is out. It's not clear if you will get the PCM at the same cost point and 4x the density of DRAM. If that happens, and that's really the promise of these technologies, if that happens, that's good. OK, so basically, that's the conclusion. You get significant energy savings also, so you can see these results. If you have 8 gigabyte DRAM versus a hybrid memory over here, your power increases, but 32 gigabyte DRAM is much, much more power hungry, as you see over here. So 32 gigabyte PCM plus 1 gigabyte DRAM is much better. An energy perspective is also much better. Your energy is much lower than either 8 gigabyte DRAM as well as 32 gigabyte DRAM, and energy delay is also much better. Sounds good, right? Oh, OK. There's also the average lifetime here. So there's a much larger average lifetime here because you have a large DRAM cache that acts as a right filter. Right? There's a huge buffer over here. Again, that's the optimistic view. If you have that hybrid memory, that's what it enables. Again, the problem is no guarantees, though, right? Maybe someone can write a program that attacks this system and causes wear-out problems. OK, so you can read this paper as well. So this appeared in the same conference at the same session at the same time. We were doing the same research at Microsoft, and other folks were doing the same research at IBM. So it was nice to see their perspective as well. OK, so let's look at the other problem. So we've discussed the write problem, writes, and hopefully this, that gives you some perspective as to what you should do to this memory. But there's also the data placement problem. And this is actually a much more general problem. It's not just DRAM, PCM, but any type of memory that may look like this, you have a data placement problem. And this is oversimplifying it, of course. This is fast and small and large and slow. And they're connected to different channels, potentially. But you could imagine they're connected to the same channel, and internally they have some connection. Again, the architecture, even the architecture is not clear at the moment. So there's a lot of potential for innovation. So the data migration problem is, when do you migrate this page, and which pages do you migrate? OK, we've discussed this. So once you actually do the migration, this is fast, you have another problem, which is maybe a load balance problem, right? If you actually are accessing only this memory, maybe that's not good also, because you're underutilizing the bandwidth in this channel, assuming your system architecture that looks like this. Maybe you should balance the load. And page migrations clearly have performance and energy overhead, assuming these are pages. So that's where the smaller granularity helps. OK, so I'll give you some quick ideas over here. But one of the ideas is, if you can somehow characterize the data access patterns and guide the data placement, you can actually do much better than otherwise. And one simple idea that's actually true for many memory technologies, if you're doing streaming accesses, phase change memory is actually almost as fast as DRAM. Why? Because you have row buffers, or you can architect it to be almost as fast as DRAM. You have, let's say, the same row buffer in phase change memory that provides data at the same rate. And if you're doing streaming, you're bound by memory bandwidth, and phase change memory is good. So you should perhaps map your streaming accesses, data structures, to phase change memory. But if you're doing more random accesses but have good locality, this is much faster than DRAM, right? Much faster in DRAM, because you're accessing the array now. So maybe you should place the data that does random access and has some locality in the DRAM. That's a very simple idea. The idea is to place random access data with summary using DRAM, streaming data in PCM. How do you determine that? There are many, many mechanisms. This paper does it in the memory controller with some tracking mechanisms, with some cost. But the programmer can mark these accesses. That's another possibility, right? So a lot of ideas can be here. But I'll point out one thing over here. If you're doing only streaming in your workload, there's nothing surprising about this in phase change memory, right? You could actually have a tape that's really slow and read it at high bandwidth. The latency may be really large, but as long as you provide mechanisms to read it at high bandwidth and enough buffering, you can actually have very good performance with streaming accesses. But random access performance is a lot harder. You really need a good technology at the array level to get good random access performance. So I think I've already given you this idea. So you can, this is basically just a more iteration of the idea. Because row hit latency is similar in DRAM and PCM, and row miss latency is small in DRAM but large in PCM. We're going to take advantage of it. Basically place data in DRAM that is likely to miss in the row buffer, because miss penalty is smaller in DRAM, and that is reused many times. That's the idea over here in this particular work. And the performance is somehow, again, this is the pessimistic view, as you can see over here. 16 gigabyte PCM, performance is here. 16 gigabyte DRAM, performance is here. And this management mechanism that's called RBLE dynamic comes somewhere in between, which is not bad, assuming this pessimistic view. OK. And you can read this paper for more detail. Any questions? This makes sense, right? Basically, the higher level idea is characterize your access patterns, know them well, and then place the data to the right place. And streaming versus random access is a very good distinction, actually. I mean, we've discussed this before, actually. If your data has no locality, how do you design the memory hierarchy, right? I posed that question. Today, we're designing memory hierarchies for assuming locality, but that may not be true for all the data. OK. Let's talk about some other things. What other things that do you need to take into account in data placement? And this is a complex problem. It's not an easy problem. But the previous things that I described to you consider heuristics, right? And they're a limited part of memory access behavior. Wouldn't it be nice if you can actually directly predict the performance impact? You have this page as a candidate, or a cache block as a candidate. The question you ask is, if I migrate it here, what would be the performance that I would get? It'd be nice to have a performance model for this. And this paper that I'm going to very briefly describe strives for a performance model. It doesn't fully develop that model. But that's usually a good thing to strive for, performance model-driven decisions for migration. For example, well, what goes into this? It's basically you consume latency, you consume bandwidth, you cause interference. But also, there's the impact of memory-level parallelism that we've discussed. And I'd like to talk about this because this happens in many, many places, including here. Basically, memory-level parallelism, you know that it's the number of concurrent memory requests from the same application when a page is accessed, right? In this case, we're talking about a page because we're talking about the page granularity migration. And this affects how much page migration helps performance. And you will empathize with this. For example, if you have this request to page 1 in memory B, it takes longer. But if you migrate it to memory A, that's fast. Now you can service those requests much faster. Now, this is good. Migrating one page, in this case, reduces stall time by some amount, right? Because that's the only page that is outstanding requests. But if you have 2 pages that are accessed in parallel, migrating one page doesn't help. Right? And you know this by now very well. This is a very similar idea. It was the MLP-aware cache replacement paper that you're reading. Basically, you need to migrate both pages. That's the sad part. So this overlap effect is actually very strong in systems. So if you don't take into account this memory-level parallelism, you may make the wrong migration decision. Even though you reduce the page access latency, your overall stall time doesn't reduce, right? OK. So basically, it wouldn't be nice if you have a generalized mechanism that directly estimates the performance benefit of migrating a page between any 2 types of memory and places only the performance-critical data in the fast memory. So if you want to know about this, you should take a look at this paper. The key idea is for each page, you calculate some utility metric, the performance impact of migrating that page from one memory to the other in the system. Now, how do you calculate that? So you should really read the paper. And you migrate only pages with the highest marginal utility, pages that improve system performance the most when migrated. So calculating that utility metric is really the key. You basically need to have a performance model that says, this is the performance benefit that I will get, including MLP, including robot for locality, including whatever that needs to go into that model. Right? And that's not an easy thing. Okay, so you can take a look at that paper. So what is the benefit of doing this? So this is the robot for locality-aware management, categorize streaming and random accesses differently and treat them differently, put the streaming access in PCM, random access in DRAM. So on top of that, you gain more performance, basically. And performance benefits increase with memory intensity. So for the more interesting workloads that access memory a lot, you get better performance benefits. So this kind of performance model-driven data placement actually does better. Of course, you're as good as your performance model, right? If your performance model is not good, then you don't gain much. And clearly, if your workload is not that memory intensive, you don't gain that much also, so because your headroom is much lower. Okay. And of course, whenever you're designing systems like this, it's always good to look at different parameters, right? So in this case, we're looking at fast memory versus slow memory. If the slow memory is a lot slower versus less slower. So in this case, the slow memory is 3x slower than the fast memory, whereas here, the slow memory is between 7.5 to 20x slower, depending on reads and writes, than the fast memory. And the performance improves better, actually, around here and less over here. So these are the kind of studies that you can do with simulation. That's the reason why this slide is over here, actually. OK. Any questions? Basically, we've been talking about this, right? The challenge is enabling and emerging technologies to augment DRAM now, not replace DRAM. We've given up the replacement for now, because it turns out to be really hard. So you need to really manage hybrid memories if you want to do this augmentation. Let's look at the other challenge, because we've assumed that you have this DRAM cache, right? That's large, and we use it as a cache. But how do you build it? Basically, the problem is a large DRAM cache requires large metadata, a store, tag store. Tag store plus block, maybe you need to keep track of block-based information to decide these migration decisions, right? Make these migration decisions. The question is, how do you design this efficient DRAM cache? When you get a load, you need to access that metadata somehow, and the metadata tells you the data is in DRAM or the data is not in DRAM. If the data is in DRAM, then you access DRAM. Otherwise, you need to access phase change memory. OK, so how do you actually, where do you store this tag information? One option is in the memory controller, you have a huge table. Maybe, I don't know, 2 megabyte table. That doesn't sound good, right? Maybe that's OK. I don't know. But as an architect, again, as an engineer, you should strive for low-cost solutions. An engineer is someone who does for a dime what any fool can do for $1 or for a Swiss franc. I think they're on par. Basically, how do you do that? One option is to actually store the tags inside the DRAM itself. That's one idea, actually. Instead of having separate storage, why not have the tag storage inside the DRAM and the refinement of the idea inside the same row as the data, as in DRAM? So store metadata in the same row as their data, and data and metadata can now be accessed together. Now, if you want to figure out whether some data is in the DRAM cache, you first need to access DRAM to get the tags, do the tag match, and if the tag match says, yes, it's in DRAM, then you need to access the same row to get the data itself. Doesn't sound too bad. Well, the bad part is you need to access DRAM before you determine whether you really need to access DRAM, right? The first access is for the tags. The second access is for the data, assuming it's in DRAM. So you need to do 2 accesses, assuming you get a DRAM cache hit. The good part is the second access is a robot for hit, hopefully, because of the way we organize the data over here. The bad part is you still have 2 accesses, even on a case of DRAM hits. So the benefit, the big benefit is there's no on-chip tag storage overhead, and the scalability issue goes away, right? Now as you add more DRAM, you also get more metadata storage, tag storage. You're as scalable as the size of your DRAM. The downside is, as we've discussed, to cache it is determined only after DRAM access, and cache it requires 2 DRAM access. So how do you solve that? Basically, the second idea is caching the tags. So caching helps. If you have locality in the tags, you cache the tags in the SRAM in the memory controller. So you have a small cache for tags, metadata, and keep it in the memory controller. Oh, that's not the idea. That's the old idea. The second idea is basically cache in on-chip DRAM frequently accessed metadata. It turns out you can actually cache only a small amount and get really good hit rate. Basically, if you have this solution, the first thing you do is you check if the small tag cache to see if the tag cache has the tag that you're accessing. Right? If you get a hit, that means that the tag is in DRAM, right? The data that you're trying to access is in DRAM. Now you can do only one DRAM access. You've eliminated one extra DRAM access to figure out whether the data exists in DRAM. Now, if you get a miss in the tag cache, it may still be in DRAM, but you don't have that information. So you have to access DRAM once to get the tag and check. And if you hit, then you have to access DRAM again, hopefully in the same row, to get the data. But if you get a tag check mismatch, then you need to access PCM. So it's a little bit more complicated, but it turns out you get about 70% or 80% hit rate in this tag cache, so you can eliminate a lot of those accesses. And if you manage it well, actually, you can get much higher hit rate. OK. So the third idea that's orthogonal to what I've discussed here is really dynamic data transfer granularity. We didn't talk about the transfer granularity, but this is also very important. Are you caching 4 kilobyte blocks in DRAM or 64 bytes? If you're caching 4 kilobyte blocks, that's a lot of data movement between two memories, right? And this is really moving data across two different channels now. That's a lot of overhead. Unless you have a specialized connection between the two memories, but that's a very different design. So it turns out, as you can imagine, some applications benefit from caching more data, larger cache blocks, 4 kilobytes, because they have good spatial locality. Others do not. Large granularity wastes bandwidth and reduces cache utilization. And one idea is have a dynamic caching granularity policy. Again, there's no magic here. The basic idea you remember, the set sampling, hybrid replacement policies in caches. You could actually do something similar. Basically, you can group main memory into sets of rows, and some of them follow 64-byte granularity, some of them follow 4 kilobyte granularity, and then you basically do a cost-benefit analysis. The rest of main memory follows the best granularity. Again, at high level, the idea is very similar, but then how do you figure out exactly how do you do the cost-benefit analysis? That's in the paper. And there's a lot of room for improvement. I just want to give you the high-level fundamental ideas. So basically, that sampling is a very general approach whenever you're trying to decide between multiple different things. In this case, we're trying to decide between multiple different caching granularities, right? OK. Just to give you some results of this, basically, this is the SRAM tag store. If you have an SRAM tag store, that's a lot of overhead in the memory controller. If you actually put the tags in DRAM, but not in the same row buffer as the data, not in the same row as data, you actually lose performance significantly. Basically, here you're doing 2 DRAM accesses to get a DRAM cache hit, but they're not in the same row. The tags are in some part of DRAM that's separate from the data. Basically, your performance degradation is huge compared to an SRAM tag store. That's why this is an important topic. But if you have put the tags in memory, but in the same row buffer, you actually gain significant performance compared to not putting the tags in the same row buffer as the data. And this is what happens. This is called timber. Basically, if you actually cache the tags in a small SRAM store in the memory controller. So you're getting closer to a perfect tag store in the memory controller. But still there is some performance degradation because you sometimes need to do 2 DRAM accesses over here. And if you do dynamic granularity, that adds a little bit on top of that, as you can see. And actually, the energy efficiency is better if you design a system like this, because the large SRAM tag store is very energy inefficient also. OK. Any questions? There's a huge design space, as you can see, right? I don't expect you to know all of the ideas. Just get the high-level ideas, basically. Caching the tags, for example, is a solution for not accessing DRAM twice. OK. Actually, this is a very hot research topic right now. People are looking at DRAM caches, and there are many, many recent options that I'm not going to cover in detail. There is actually, for example, how do you handle large page caching? How do you handle 1 megabyte pages? How do you handle the DRAM cache hits, cache misses, replacement traffic? How do you do the replacement decision? Is it hardware managed? Is it software managed? ... All kinds of design decisions over here. One of the other ways of eliminating the tag store is augmenting the virtual memory management system. And some works actually follow that over here. I'm not going to go into much detail. If you're interested, you should read this paper. This is the state of the art, actually. By the way, I'm not going to be here next week because I'm attending this conference that's mentioned over here, Micro, in the US. But we will still have lectures. We'll be presenting this paper and the Ambit paper that you're actually reading. But basically, the idea, one of the ideas in this paper is you track the presence in the large DRAM cache by using the translation look-aside buffers and page table. You get rid of the tag store, but append the tags into the TLB. So whenever you access to do virtual memory translation, the TLB also says, oh, is it in your DRAM cache? 1 bit, let's say. If the answer is yes, then you directly access the DRAM cache. If the answer is no, then you don't. Basically, the realization is that you already have a huge tag store, which is the page table. Right? That's for your entire memory. If you augment it a little bit, then you can get rid of that hardware tag store, maybe. Now, the problem over here is whenever you do this, you have a problem, because what if somebody changes the mapping? Right? If some processor changes the mapping, and if some other processor already cached that mapping meaning in the TLB, you have the virtual to physical mapping, page table entry, right? If this processor changed the mapping and cached the data in its DRAM, and this other processor already had the mapping in its TLB, now you have a problem. This may have the wrong mapping, right? This may think that the data is in some memory, whereas this processor brought that into its own DRAM cache. So you really have a TLB coherence problem, which is not handled in today's systems. Today's TLBs are not kept coherent, actually. Well, kept coherent with a really, really slow method called TLB shootdown, which I'm not going to go into detail. Basically, whenever you change a mapping in the TLB, you shoot down all of the other TLBs. Not so good. It's very slow. So the other thing in this paper is really how do you actually do that TLB shoot down or do some lightweight TLB coherence. And this requires some support in the memory controller. So in the end, you need some hardware support to do this. So this requires some support in the memory controller to actually do this coherence. OK, and there is some more in the paper. But basically, this is the state of the art right now. You can so this is the speed up that you get compared to some other DRAM cache management mechanisms. And again, this is also the speed up by varying the DRAM cache bandwidth and latency. OK. In the last 2 minutes, let me give you some other opportunities with the emerging technologies, and then we will conclude. Actually, I'm not sure if it's 2 minutes. OK, 4 minutes. Any questions on the previous one? OK. So there are a bunch of other opportunities. I'll go through some of these very quickly. I'll talk about the first one over here, merging of memory and storage. Because we have persistent memory now, why don't we merge memory and storage? Why don't we have a single interface to manage all data? And this is actually a longer description than what 4 minutes allow. But we've been used to this two-level storage model where you have a storage device that's separate from the memory device, right? And that has led to 2 different interfaces. But non-volatile memory actually has the characteristics of both the storage device and the memory device, main memory device. It's fast, it's byte addressable, and it's non-volatile. It's not slow. And the device can actually give you 1 byte at a time, right? It's like DRAM. It's not volatile. Traditionally, we've been used to this two-level storage model where main memory is accessed with loads and stores, and volatile data is stored there, and persistent data is stored in the storage device, and you access it through a file system interface. Even at the programming language level, you cannot access persistent data directly with loads and stores today. And this has evolved because the devices had very, very different characteristics. This was really fast. This was really slow. Now, even with SSD, this is really slow. So there's a lot of overhead over here. Whenever you open a file, for example, there's a lot of buffering that happens. You make copies, and you bring data into the main memory, actually. And then it gets buffered so that you can actually do things fast, and then you write it back. But if this is replaced over here with something as fast almost as this other device, now this becomes a huge bottleneck. Basically, the operating system and file system code to locate, translate, and buffer data become performance and energy bottlenecks. And wouldn't it be nice, actually, to unify memory and storage management in a single unit to eliminate all of that wasted work? Basically, you do loads and store, and you could decide whether it's persistent or not, but you basically have a single interface to access these devices. And I'll show you some examples that show that this improves both energy and performance and simplifies programming model. Well, I'm not going to show you examples with the simplifying programming model, but I'm going to show you an example of the programming model. Basically, you can manipulate persistent data directly. You don't need to, let's say you don't have a file. You say this is a persistent array, and I'm going to update that array. And it's going to stick forever, as long as I don't update it again. That sounds nice, right? We cannot do that today directly at the array level. We have to write into a file and then do that update and write it back, read it from the file later on. So this is one example of a persistent array, for example. You can have a persistent object. It's a different programming model, of course. And you basically write the data into that persistent object, and the value becomes persistent. But the persistent memory manager, underlying devices can be very heterogeneous, right? It could be some phase change memory, maybe, some flash, hard disk, DRAM. It could actually take advantage of the different characteristics of this device as long as it gets good information from the programmer. So programmer may say, for example, this data doesn't need to be persistent, so I'm just going to do a load and store, so you can keep it in DRAM. Or maybe this persistent memory manager can figure out that it can keep it in DRAM. So what's the benefit of this? I'm going to skip this so that you can read it. But to motivate you, again, basically, programmer can categorize their data over here. But let me give you the benefit of this very quickly, and then we're going to pick up and look at this. So this is a hard disk-based system for one application that you can read in this paper. It's very storage-bound. So most of the time, the application waits for the disk to return data. Now, if you replace the hard disk with phase change memory, it turns out you get a lot of benefit, 24x, just because of the device. You don't change anything else in the system. This has DRAM in the system. So now you still have two different models, basically. DRAM is accessed with loads and stores, and NVM, phase change memory, is accessed with the file system interface that we have today. Now the bottleneck actually shifts. The bottleneck is actually in the system calls over here now. Really, the operating system is your bottleneck. You cannot see it in this little thing because it's dwarfed by this. But if you actually get rid of DRAM in the system, we're getting rid of the fast memory, but change the model such that you can do loads and stores directly into the non-volatile memory, phase change memory, you actually get 5x more performance benefit. That sounds nice, right? You're getting rid of the fast memory. Everything is becoming slower. Well, everything that used to go into DRAM is becoming slower, but you're getting rid of a lot of overhead of manipulating persistent data. Now your software is not bottleneck. You're directly accessing the persistent storage with loads and stores instead of going through the software, file system calls, operating system calls. So that gets you 5x. Now if you add back DRAM, you'll get even more, but we can talk about that later. So the energy is similar. Basically, this is hard disk for that workload. If you replace it with non-volatile memory, you get about 16x. And if you actually get rid of the two-level interface, have a single-level interface, and get rid of DRAM also, just have non-volatile memory, you get about 5x again over here. Now, if you're interested, you can read that paper. But one big challenge and opportunity with some of these emerging technologies, actually all of them, I think, is how do you combine memory and storage together? Because this could actually lead to huge benefits if you can do it. And this could enable a unified interface to all data. Now, this is actually not that new. Old systems like the Atlas computer, for example, had a unified interface to all data. You could access everything with loads and stores. The reason the file system interface got developed is because the technology got bifurcated, and DRAM became really fast, and these persistent devices became really slow. And as a result, people developed these two different interfaces. Now, if things go back again, and devices are similar in terms of latency, and of course they provide the persistence as well, maybe you can access the data with a unified interface, loads and stores. Now, there are implications on the programming model and the upper layers that we're not going to talk about over here right now. Any questions? Hopefully I've challenged you a little bit in the thinking of how we design the systems today. Okay, if there are no questions, tomorrow will be a discussion session. So come with questions on the labs, homework, lectures, anything. Probably labs. If you're doing the labs, then I would suggest that you start doing the labs. But it's really a lab session that you can work with the TAs. But homework is also fair game. Okay. Sounds good. See you later.